Hey, it's Bruno here. I'm so impressed with you. You've done so much good work for us that we're going to move you to a big client of ours. This is our most important client, so we really can't screw this up. Now, this client manufactures construction equipment, and they have some data around bulldozers, which they need to run their business. They need to figure out some bulldozer pricing so that they can improve their business. Now, this client is super important to us, so we need to make sure that this project is top-notch and we create a model that they're going to be happy with. And obviously, I thought of you. I really believe in you now, so we have a deadline tomorrow. Let's finish it, and I can't wait to see it. All right, there goes Bruno, being all demanding and giving us a deadline, but you know what? We have the skills necessary now to deliver on this big project. We're going to predict some bulldozer prices. That sounds fun, doesn't it? And we're going to learn about something called time series data, which is very, very common. It's going to be another fun one, so let's get started.
Hello, and welcome back to our second structured data project. Now, this one's really exciting, right? Because we're going to be predicting the sale price of bulldozers. Who doesn't love bulldozers? I remember when I was a kid, I used to have all these tractors like Tonka trucks and used to play with them all the time. And this one's a little bit different. Of course, it's a regression problem because we're trying to predict a number, aka the sale price of bulldozers. But what we're going to do is we're going to take data, and in this case, the data, see this little clock emoji, it has a time component to it. So that means in our previous project, there was no time series. It was just a big static data set. Whereas this one, there's a sale date component, which means that a bulldozer has been sold on a certain date. And so what we'll be doing is using sales from the past to try and predict sales in the future. And that's our problem definition, right? Is we'll take our data, which is full of bulldozer sales, and we're trying to predict the sale price. And I mean, you might be looking at this emoji and going, that's a tractor, Daniel, that's not a bulldozer. And yeah, I know, there's no bulldozer emoji, sadly, yet. That may be an update coming from Apple, but who knows, fingers crossed. Of course, we're going to use our 6-step machine learning framework. We'll start by defining our problem, which is, of course, seeing if we can predict the sale price of bulldozers. We'll have a look at some data. We'll find an evaluation metric which is suitable for our problem. We'll then have a look at the features of the data. We'll, of course, try some machine learning modeling because, after all, that's our goal, is to build a machine learning model that helps us to predict the sale price of bulldozers. And throughout the entire session, we'll be doing experiments. Now, we've seen what tools we can use, and we're going to be using the exact same tool set that we used in the previous structured data project. So we'll have Pandas, Matplotlib, and NumPy for data analysis. We'll be working within the Jupyter Notebook using our Conda environment, and we'll use Scikit-Learn for any machine learning modeling. Now, because this is a new project, we'll approach it as if it's a new project. We've got our steps to take in a new project here, but we've been through these. We've got our computer, we've downloaded and installed Miniconda. This is where we're at now. We're starting a new project. So we'll create a new project folder. And now, of course, because we're using the exact same tools as what we did in the previous structured data project, you could complete this entire project, the bulldozer sale price prediction, in that previous folder. However, for completeness, we're going to create a new project folder. We'll download our data from Kaggle. We'll get to that in a second. We'll create an environment which holds all of our tools that we'll be using. We'll use our Jupyter Notebook as our workspace. We'll perform data analysis and manipulation using our NumPy, Pandas, and Matplotlib tools, and then machine learning using Scikit-Learn. Now, of course, if you do get stuck, and don't worry, you probably will, I get stuck all the time. The steps that you can take is to follow along with the code as best you can. Try it for yourself. Remember our motto, if in doubt, run the code. Then if you want to find out more about what a function is doing, remember to press Shift and Tab to read the doc string, which will give you some information of what a function is doing. If you're still stuck then, of course, don't be afraid to search for it, right? You'll come across resources like Stack Overflow, the documentation for Scikit-Learn, Pandas. And then, if you've searched for it and you find some information, maybe you copy it from the documentation into your Jupyter Notebook, then of course, try again. Remember, if in doubt, run the code. And if you're still stuck, never be afraid to ask a question. If you're sitting on something and you're thinking, oh, I wish I knew the answer to this. I wonder, I can't find it anywhere. Just ask, right? If you're running into an issue like that, more than likely someone else is running into a similar issue. So don't be afraid to ask. Post a question. You can go to Stack Overflow or Discord or anywhere else you can ask a question. Never be afraid to ask a question. All right. With that being said, let's not wait any longer. Let's get our project folder set up and get into the second project. Now, since we're starting a new project, it makes sense to take the steps in starting a new project. We're up to here. What we're going to do in this video is create a project folder, get our data ready, create an environment, and then launch up a Jupyter notebook and make sure that we can import our tools so they're ready to use for our problem. So let's get started. I'm going to go to my desktop. I'm going to come to my machine learning course folder that I've been using. I'm going to make a new folder, and this one I'm going to call, let's call Bulldozer Price Prediction Project. Nice and simple. Have I got any spelling errors? Nope. Beautiful. So we'll come into this folder. Beautiful. We've got an empty folder. So if we go here, we can tick this one off. So create project folder. Now for the data, this one's a little bit different. We're going to go to Kaggle to get our data set. Because what the bulldozer problem is, so if we go to kaggle.com, Blue Book for bulldozers. Now this problem that we're working through originated as a Kaggle competition. So you can see here, predict the auction sale price for a piece of heavy equipment, aka bulldozer, to create a blue book for bulldozer. Now I'm assuming a blue book means maybe historic sales events or something like that. I'm not entirely sure. So if we look here, we can see an overview of the project. When this competition first came out, there was a $10,000 prize pool for this competition. And if you're wondering, hey, I'm not even sure what Kaggle is, well, you can imagine it as the home for data scientists, because Kaggle is full of different competitions, different data sets, different notebooks and discussions, as well as heaps of courses as well. Kaggle is just a plethora of resources for data scientists. And if you're wondering what the competitions are, well, this is one here. What happens is a company might post a data set, and then it'll be your job to see how well you can model it or how well you can build a system to solve the problem that they're posting. And that's what we're going to be working through in this project. We're going to download the data, the data set from the original competition, and then we're going to build an entire project to end up building a machine learning model, and we'll see how we would have ended up on the leaderboard. So you can see here we've got some scores, and these are different teams of people around the world, of data scientists just like you. So that's what we'll have by the end of this project. But if you're talking too much, let's get the data. So you can come to this URL here, kaggle.com/c for competition /bluebook for bulldozers /data. You can click this download all link. Now you will need an account to log in to get this data, but since I'm already signed in, I'm going to download it. We can see that it's going into my downloads folder. So if we come back to my file browser, you can see I've actually already downloaded it here, but this is just going to re-download the exact same file. So there we've got it there. Now we could keep it here, but since we're working in our project folder, I'm going to move it into the Bulldozer Price Prediction Project, the folder we just created. So your folder might be differently named. Now we can see here, beautiful. We've got our zip file. Let's unzip that. Wonderful. And that comes into a folder of more folders. Far out. We've got train invalid CSV. And if you're looking through these wondering what's going on, well, the next place to look is back in Kaggle and see what's going on here. So we've got data description. What I might do is zoom in. There we go. Pinch to zoom. Come on, Daniel, you know how to use a computer. Okay, so this is what it's telling us. The data for this competition is split into 3 parts. And remember how I said that this is a time series problem? Well, we've got train CSV, which contains data up to the end of 2011. And then we have valid.csv, which is the validation set, which contains data from January 1, 2012 to April 30, 2012. Now you notice here that the validation set has data after the training set, which is from 2011. We'll have a look at this when we're working through it. And then finally, the test data set, which won't be released until the last week of the competition, but because this competition has already passed, we've got access to the test.csv. It contains data after the validation set. So see here, the validation set ends on April 30, 2012, whereas this one continues from May 1, 2012. Okay, so this is some information here about the data we're going to be working with. There's also a data dictionary, but we'll have a look at that in a second. Let's go back to the folder we were working with. And if we look here, train CSV. Where's train CSV? It's still in a zip file, so we'll unzip that. Train.csv, wonderful. Then we've got valid.csv. Okay, so this one must be train and valid.csv in the one file. We'll have a look at that in our Jupyter Notebook in a minute. We're just familiarizing ourselves with the data we've downloaded from Kaggle. Then we can see data dictionary. Okay, that's pretty self-explanatory what that might be. And then there's test.csv. Okay, so we've got that. All right, now let's go back to our project folder that we're working on. What I might do is put this, sticking with the folder nomenclature, which is a fancy name for naming system that we've been using, we might create a data folder and just put all of our data in there. And then we can delete this zip file because we've got Blue Book for Bulldozers in there. Wonderful. Now we've got a file to work with. We come back here. Bulldozer price prediction project. We've got our data. Let's go back to our workflow. We've got our data in our project folder. Excellent. The next is to create an environment or collection of tools using Conda. Let's do that. And to do that, we're going to have to use terminal. Make this window a little bit bigger. So I'm going to change directory into my desktop, which is where I'm storing this folder. Come back into terminal. So change directory, desktop, ML course, and then within that, I've got Bulldozer price prediction. Wonderful. And so I've got to go ls. It shows me that I have this data folder, which is exactly what we've got there. Wonderful. And so now we're going to create an environment. So we can do that with Conda create. And because we want to create a little n folder, actually, I need the prefix tag. Now we've seen this in our previous project, but we're going to create a new environment within here. So let's do that. So Conda create prefix .env, yes, correct. And then we're going to give it Pandas, NumPy, Matplotlib, Jupyter, and Scikit-Learn, because we're staying in line with the tools that we want to use. So Pandas, Matplotlib, NumPy, Jupyter, Miniconda is what we're using to create this environment, and Scikit-Learn. So let's see if it works. Beautiful, and we're going to press yes. And there we go. So I'll let this load for about a minute or so, and I'll come back once it's finished. Beautiful. So that took about a minute or so on my machine. It'll depend on how quick your machine is or how fast your internet connection is, because Conda has to download a few things. So we can see to activate this environment, which we've seen before, we can use the code here, Conda activate users, Daniel, desktop, machine learning course, Bulldozer price prediction, project/env. And if we look back into our folder that we created, we've got an N folder, which in here is going to contain all of our tools. So let's activate that and see if we've got a Jupyter Notebook ready to use, which we won't, but we'll start up a Jupyter server so we can get started in our workspace. Desktop/ML course/Bulldozer price prediction project/env. Wonderful. So you notice here that the base has now changed to this file path here. And to test if we've got Jupyter installed, we can type in Jupyter Notebook. What this is going to do is create a server on our local machine, aka this computer right here, running Jupyter, which is where we can start Jupyter Notebooks and get our workspace up and running. Beautiful. So that took about 30 seconds or so. The first time you run it in a new environment, it may take a little while to load. Now we've got the exact same folder that we created in our File Explorer, or Finder in my case, up on Jupyter. Wonderful. And the way we can test to see if our environment is set up correctly, so we can go new notebook. Wonderful. And to test it quickly, we're going to go import NumPy as NP. We need to check that we can import all of our tools. Pandas as PD. Import Matplotlib.pyplot as PLT. Import Scikit-Learn. Now, if it's worked correctly, this cell should run without any errors. Now, again, this might take a little while if it's the first time running in this environment, as Conda and Jupyter prepare all these tools. So we'll just wait patiently while this runs through. Beautiful. So again, on my machine, that took about 30 seconds or so, maybe closer to a minute. But what this means is we've got our tools ready to use. So if we come back to our workflow, we've just imported Pandas, Matplotlib, NumPy, and Scikit-Learn, and we're working within a Jupyter notebook. And we've gone through these steps here. So we've created a project folder, we've downloaded our data from Kaggle, we've created an environment which is a collection of tools, we're working in a Jupyter notebook, and now we have access to these tools here. So this is what we're going to do now: data analysis and manipulation, and of course, finishing off with some machine learning. Well, our notebook's ready to go. This is what we're working for the next few videos. So I'll see you then. Beautiful. Now we've got our Jupyter notebook set up and our tools are importing thanks to installing them with Conda. Let's give this bad boy a name. So end-to-end bulldozer price regression. Nice and simple. Wonderful. And what we're going to do is we're going to start off by bringing in some headings to our notebook so we have some structure of what we're doing. And the ones we're going to do is we're going to bring this framework in. So we'll get all these 6 steps here: problem definition, data, evaluation. We'll check out Kaggle for what evaluation metric they use, features, modeling, and then experiments. So let's do that. We'll create a new cell above here just to prettify our notebook. So what can we start this off with? We'll give it a nice title. So predicting the sale price of bulldozers using machine learning. Let's put a little emoji here. There we go, frequently used, good one. We'll turn this into Markdown, wonderful. So in this notebook, we're going to go through an example machine learning project with the goal of predicting the sale price of bulldozers. Nice and simple, right? We want to get into modeling and to working on code as fast as possible. So this is just, these kind of layouts is just to help us out in the beginning. So problem definition, what was the next one? Data. Number 3 is, see, I can't even remember what the top of my head. Let's go back. Remember, this is why we have this, so we can check it out. Evaluation. Had a mind blank there. But these things will happen, right? Whenever you dive into every project, it's not going to be like you know everything of what to do off by heart from the very start. That's what machine learning is, experimentation, features. Let's go through these, and then maybe down here somewhere will be modeling or whatever, but we'll wait till we get to that point. So let's define our problem in a single sentence. We'll go back to Kaggle. So if we go to the overview, there we go. We could just put in that, but we'll rewrite it in our own words. That's a bit more fun, isn't it? So we'll come here. What could we call this? Put it in a quote. How well can we predict the future sale price of a bulldozer given its characteristics and previous examples of how much similar bulldozers have been sold for? Does that make sense? So our goal here is to use some data to build a machine learning model to predict the sale price of bulldozers in the future. And now data. Now we've already imported this. So if we have a look at Jupyter Notebook open, we've already got this open here. We don't need an extra window. Let's have a look at data, Blue Book for bulldozers. There we go. So we've got train invalid, train. All right, so we might just put a link in here. So we go, the data is downloaded from the Kaggle Blue Book for bulldozers competition. And then you might come into this Kaggle competition And they've already given us some information, so we might just put something like this. So we might just copy this to remind ourselves of what train, valid, and test is. Again, this will be different depending on whatever data set you're working with. We'll put it in here. So train, valid, and test, just so someone who is new to this would be able to go through our notebook and go, oh, okay, I see what's happening. There are 3 main data sets. And we're just going to put the link in here. This is all part of communicating your work, right? So that's what you want. When you're doing things in machine learning or any kind of coding project, it can be easy to sort of get lost in making your own sort of projects, and then someone else gets upon it, and because you've done it all in your own style, they're going to be like, oh wow, what's going on here? So this is what we're trying to do. We're trying to help our future selves as well as anyone else we'd share our work with. So evaluation, we can come to Kaggle competitions. Whenever a competition is posted on Kaggle, there's going to be an overview. There's going to be some prizes. There's going to be a description of what's going on here. And there's going to be an evaluation. So how do you win the competition? So here is where we'll be shown the evaluation metric for this competition is the RMSLE, or root mean squared log error. Wow, that's a mouthful. Between the actual and predicted auction prices. See, that's what all evaluation metrics are, is a comparison between the actual and predicted auction prices. So what we'll do is we're going to copy this in here. There we go. RMSLE. And don't worry, we're going to have a look at that. We haven't actually gone over what RMSLE is, but we have gone over mean squared error. Now, you might be able to infer from this that root mean squared log error is just the root of the mean squared log error. But we'll have a look at that when we come to evaluation. For more on the evaluation of this project, check. We're going to put another link in there. Boom. So as our goal with most regression metrics, we might put it in here. Note, the goal for most regression evaluation metrics is to minimize the error. For example, our goal for this project will be to build a machine learning model which minimizes RMSLE. So that's for regression metrics, right? If you have mean absolute error, MAE, or mean squared error, your goal is often to minimize it. And now features. So this is where we want to have a look at what different parts are there of the data. So if we come to Kaggle and we have a look at data, this data set comes with a data dictionary. And the good thing is that we've downloaded that. It's in the form of an Excel file. That's the extension for Excel. Now, I don't have Excel on my computer, but the beautiful thing is you can open Excel files in Google Sheets, which is what I've done here. So what we'll see is we haven't imported our data set yet, but these are the different columns. We'll have a look at it in a second. And what this is going to tell us is, okay, so this is the sales ID. That's a column, sales ID. The description is unique identifier of a particular sale of a machine at auction. Wonderful. So I might copy this. Anyone with a link can view. Beautiful. And go put it in here. Kaggle provides a data dictionary detailing all of the features of the data set. You can view this data on Google Sheets. So I'll put another link there. Beautiful. So that way we sort of know what's happening there with what's going on. And we haven't done much at all here, right? We haven't explored these at all, but what I prefer to do is just set out this little layout and then get cracking on the code as soon as possible. We'll finish this video there. So we've gone through steps 1 to 4. Nice and simple, right? We've defined our problem, so we know what we're doing. We know where the data's coming from. We know what evaluation metric we're moving towards thanks to Kaggle. And thankfully, Kaggle have provided a data dictionary for us. And these things, you won't always get them like from the start as simple as this. So this is where it might take, if you didn't have these things, if you didn't have a problem definition, if your data wasn't in one source that you could easily download from a link, or your evaluation metric wasn't just given to you. Same with the data dictionary. These are things you might have to do some research to do. But luckily for this particular project, we have them already. So without any further ado, since our tools are ready, let's import the data and get started on it. All right, so now we've got our notebook a little bit laid out and we know what steps we're taking, we know what problem we're trying to solve, we know where our data is coming from, we know our evaluation metric and the features. Let's import the data and get started. So in my case, we've imported it to a folder called data. You might have created a folder the same. So when I write the file path, your file path might be different to mine, but mine's going to be called data. So let's do that. And we're going to import the training and validation sets to begin with. If you're wondering why we're importing them at the same time, this will seem clear in an upcoming video. So you'll just have to trust me for the time being that we're importing both in one set. If we go Blue Book, we can probably use tab order complete. Surely. There we go. So we want train and valid.csv. Wonderful. We hit Shift and Enter. Now this might take a while because, as we'll see in a second, this is a fairly large data set. We're getting a warning. What do we have here? D-type warning, columns 13, 39, 40, 41 have mixed types. Specify D-type option on import or set low memory equals false. So if we go here, we can get rid of this warning by setting low memory equals false. So what this is essentially saying is when Pandas read CSV, when this function is instantiated, depending on how large your data set is, because data frames live in RAM, Pandas tries to minimize the amount of space they take up. So what we're doing is we're just setting low memory to equal false to go, hey, we know you're trying to minimize space, but don't worry too much. We've got plenty of RAM space. So this should work. We should be able to get rid of that warning. Wonderful. So this is just saying store it however you want to try and import it. Don't try to minimize the space that you're using. Wonderful. And the first thing we'll probably do is go df.info to get a little bit of information of what's happening. So there we go. We can have a look at that. It is the biggest data set we've worked with yet by a fairly long shot. We have 412,698 rows. That is a lot of rows. And 53 columns. Remember, if we have a look at our columns, these are our variables and descriptions. So we should have sales ID. Yes, that's a non-null integer. Machine ID, which is the identifier for a particular machine. Machines may have multiple sales. Okay, so that means a machine could be sold multiple times over the course of a time frame. Then the one we want to probably pay most attention to, because it's a time series, aside from the sale price, that's how much our machines have been sold for, is the sale date. So this is when the machine has been sold. So if we have a look at this, sale date, time of sale. Beautiful. Okay, so what can we do? Now, since sale date is a date, what we might want to do is pass it as a date, but we won't do that yet because I want to demonstrate something. So we're going to set up a plot, because this is what we usually do when we first begin any kind of project, is try to make some visualizations. Looking at this, there's a lot going on here, right? Like you could just look at this. This is hard to infer. If you're like me and you're just looking at lists of words and numbers and you're just like, I need to visualize things. I need to look at things. But we can see, actually, what can we see from this? So we've got 412,698 entries. These are non-null. We see we got some missing values, especially for usage band, whatever that is. So if we come up to our data dictionary, usage band, so value, low, medium, high, calculated comparing this particular machine's sale hours to average usage for the FI base model. So the FI base model is probably another feature. There we go. Disaggregation of FI model description. Far out. We've got a fair few pieces of information here about our bulldozers, right? So this is actually a pretty good data set. But we can see that for usage band, there's a fair few missing values because there's only 73,670 non-null objects. So that means there's 412,698 minus that missing values. And we can figure that out. Actually, before we plot, let's figure that out. So we go df is NA. This is how we're going to check if there's null values. There we go. So usage band has 339,028 missing values. Knowing what we know about machine learning models, that's something we're going to have to take care of before we can build a model. But let's push forward. Let's plot. Because we're trying to predict sale price and we know that our data is a time series, what we might want to look at is something like comparing sale dates with sale price. And because there's so many rows here, if we were to do that, if we were to try plot all of these data points in one plot, because you imagine trying to draw 412,000 dot points on a plot, your computer's going to have a hard time. So let's do about 1,000 or so. Why not? Let's go sale date. We go here. We'll do the first 1,000. How about that? That's a fairly large number. We want to do sale price. And if you want to find out the names of different columns, remember you can always go df.columns. So what we're doing here, we're taking sale date, wherever that is, sale date there, which is, if we come to our data dictionary, this is where we want to be referencing. So the time of sale, so the date that it's been sold, as well as sale price. Now, is that in our data dictionary? I think that's pretty straightforward, actually, what sales price is. Oh, there we go, sale price. Cost of sale in US dollars. So let's check it out. Let's check when have these been sold. We're going to put the sale date on the x-axis, because remember, scatter is XY, and sale price on the y-axis. So let's check it out. What have we got here? Oh, we've got our equal sign. Whoa. So you see here, we tried down the bottom to put sale date, the first 1,000 examples. So this is why our plot is looking a bit funky. And it's just trying to pack in, if we have a look at our data frame, df.saledate, that's what it's trying to plot on the x-axis. If we have a look at the first 1,000, it's trying to plot all of these values along here so you can see how it just looks like one big chunk of a barcode and then just a big chunk of black text there. So what we might do is, let's just plot a histogram, because we always like checking the distribution, which is the spread of data of as many variables as possible. But in this case, why not do sale price, because that's our target variable. So sale price. And now again, if it seems kind of unstructured what I'm doing here, it's because it really is. Like, there's so many different ways you can explore a data set. One of the best I like is just df-info. Check to see if there's any null values, so we know null as in NA, as in missing values, so we know how many missing values there are. Check the columns. Plot one of the most important columns from, now I've just chosen sale date because it's a time series problem. Plot one of the most important columns versus the sale price or versus the target column, and then do a distribution of a few columns of your choice. These are kind of the stereotypical things that I like to do when first exploring a data set. But what we can see here, we can see that most of our sale prices are below 20,000 US dollars. So the biggest column here, or not most, but a large majority, a large portion. And then we got some below 30,000. Let's just assume that's 30,000, 40,000. And then it just keeps going off, and there's less and less and less. And there's not very many that are costing upwards of 100,000 US dollars. So that's what we're looking at there. Okay. Now, what we might do is, because these dates aren't really in a format that we want them in. So see how they're in D-type object? When you're dealing with time series, you want as much information to be encoded in the dates as possible. So that's what we'll do. A little way that we can do this is called parsing dates. So let's have a look at what this looks like. Parsing dates. So when we work with time series data, we want to enrich the time and date component as much as possible. And you might be thinking, well, how do we do that? Well, let's put it here. We can do that by telling Pandas which of our columns has dates in it, using the parseDates parameter. Wonderful. And what this is going to do is turn whichever column we pass to parseDates into a datetime object. So let's first see what is a datetime object in Pandas. We got here timestamp to datetime. So you could find out a whole bunch of different things what datetime here is. Datetime object. Timestamp is a Pandas equivalent of Python's datetime, and is interchangeable with it in most cases. Okay, beautiful. So basically, when we run this, so let's do it again. Import data, again, but this time pass dates. Remember, if in doubt, run the code. So pd read CSV, and we're going to go data, bluebook for bulldozers, tick, and we're going to go train and valid CSV, wonderful. But this time we're going to pass it low memory equals false, so we don't have that warning. And then we're going to pass it pass dates, and we'll pass it the column name sale date. Why? Because that's where our dates are. And so take note of what this is. So if we go sale date, it's a D-type object. We might just put a little here, .dtype, D-type O. So when we do this, let's see what the difference is. Now this is going to override our original data frame, so we can go df.saledate.dtype. Ah, that's a bit funky. What if we did df.saledate? What does it look like? df.saledate, first 1,000. Ah, okay. So if we come up here, we got sale date. See how they look like this? What Pandas has done is, because we've passed it to pass dates, it's gone over all of the values in the sale date column and converted them into this style. So we've got year, month, day. And we can see that the data type is date time 64. And if you were to Google, compare these two, because you might be wondering, why does it have a different value here compared to here? You'll find that in NumPy, these two are equivalent. So you'll just have to take my word for it. You could Google it, or we might actually do that just so I can prove to you. So we go here, Control C. So what data type is? There we go. Date time 64 is a general D type, while M8NS is a specific type. There we go. This is Stack Overflow. So this is just a workflow, right? Of when you don't get something, there we go. np.dtype datetime 64 equals np.dtype m8. That's what we're after. But now that our dates have been passed, let's do the same plot that we did before. So fig ax equals plt.subplots. Wonderful. And we're just going to do the exact same thing, ax.scatter. We'll finish up this video in a second, actually, because we're not in a rush, right? We're learning, we're exploring. Sale price, and then we'll go here, we'll do 1,000 and see what looks different. Wonderful. So see how down the bottom now, instead of when we come back up here, we've just got a whole bunch of black because we're trying to put all these down there. Because our sale date column is now in the form of a datetime object, Matplotlib is able to intelligently look at the data type and then plot it accordingly. So we got here prices. So we can see there's a lot of sales. Maybe 2005 something happened, so there wasn't many sales in 2005. 2008, I believe that might have been the financial crisis or something like that, so there wasn't too many sales here. And then again, that's between 2008 and 2009. We can see the highest sale was done just in 2007, and then there's a lot of sales around the middle of between 2009 and 2010. But again, this doesn't really tell us too much, right? We're just getting an idea of what's going on. So let's have a look one more time, check it out. df.head, this is our data frame that we're working with. We've got sales ID, sales price, a whole bunch of different columns here. We can see that there's a whole bunch of missing values. And if we wanted to find out more about what undercarriage pad width means, remember, we've got our data dictionary. We could have a look here. There we go. Machine configuration, width of crawler threads. Wonderful. So now we've done a little bit of exploration. What we might do is sort our data frame by sale date and then keep going from there, make some more changes. So we'll do that in the next video, but otherwise, have a go at exploring the data frame, importing it, and trying to pass the dates with sale date and don't pass the dates, and check the difference in data type when you do and don't pass dates. Now we've got our dates column passed and it's in a good format that we can work with, a Pandas datetime format. Let's keep modifying our data frame so that we can work with it and eventually build a model. So we can see here we're viewing the first 5 rows and we got 53 columns along here. But what you'll notice in the middle, when there's too many columns to display in a Jupyter notebook, it truncates it. So we got ... But if you wanted to see every column, a trick you can do is df.head and then .t for transpose. So now we'll see the first 5 rows across the top. These are columns now. And if we scroll down, these are all of our columns. So we can see all 53 there, and we can see there's a fair few missing values up towards the back end here. Now this might be different depending on what rows we're looking at, but that's just a little way. If your data frame is getting truncated, you can try to transpose it and you might be able to view them all in one hit. This could take us a fair while if we're going to go through each and every single column trying to figure out what's going on. So maybe to begin with is, let's just check out our sale date column to remind ourselves of what it looks like now. Let's check out the first 20 or so. Wonderful. So we've got different dates, but you can see we've got examples from different years, different months, different days. What would be better would be if it's all in order. That would make sense, right? If our data frame was from the top, from row 0, all the way down to the bottom, it was in order. So this is the first date, and then as the examples went on, as rows went on, the dates went up. So let's do that. So what we might do is go sort data frame by sale date. This is good practice for a time series problem, right? It's a good idea. Usually with a time series problem, you're trying to use examples from the past or past events to make some inference or predictions on future events. So it's always a good idea to sort your values by the date that they occur. So what we'll do is when working with time series data, it's a good idea to sort it or sort it by date. We just go there by date. So we can do that with a little pandas function. So what we might do is go sort data frame in date order. And we'll go df sort values. And we'll go by. This is where we pass it a column name. And then we want to do it in place. Remember, in place is just going to make our change. If we didn't have in place equals true, we'd have to go df equals that. But we'll just do it in place because we do want our dates to be in order. We'll do ascending, so we want it to go from smallest date to highest date, equals true. And now, because we've passed our dates, and passed, I mean passed as in P-A-R-S-E-D, we can run these sort of functions, sort values, because Pandas is going to understand sale date as a date time object. So it's got some special properties about that. So we go here, sale date.head. So what this is going to do is going to sort our data frame by sale date, starting with the earliest date first, hopefully, if this works. And then we'll view the same 20 rows, or we'll just call the same line of code to view the first 20 examples and see what's changed. Wonderful. So these numbers on the left here are the index. So the index of the rows that we've just sorted. So df.head. So the original index of that row is 205,615. But the sale date was 1989, or the 17th of the 1st, 1989. So now you see how instead of having our dates scrambled, we've got them in order. That's exactly what we wanted. And now what we might do is it's also good practice to make a copy of the original data frame. And why is this? So we make a copy of the original data frame. We'll see it in a second. So when we manipulate the copy, we've still got our original data. So if we do something wrong on our copy, when we're exploring our data or when we're manipulating it, we can still always revert back to the original data frame. So what we might do is make a copy, and you can call this whatever you want. I usually call it something like df temp, as in data frame temporary. You can call it df experiment or something like that. Just something simple that you can remember. We're going to use df.copy so that it's basically just going to say, hey, take the data frame we've been working with, including the changes that it's in order, sale date, and just make a copy of it and save it to the variable df temp. So let's do that. Wonderful. So if we check just to make sure, df temp.sale date. Oh no, we want just the head. There we go. Exact same. Wonderful. And we can also, it's just the exact same copy of the data frame. But now, if we make changes, and that's what we're going to do, we make changes to df temp, those changes won't be reflected in df. If we ever need to, we can revert back to df as our original, and we can manipulate df temp as much as we want because we know we've still got the original. So, beautiful. Now we've got df temp. What we might do is, although we've ordered our data frame by date, we might use these dates to enrich the data in our data frame. And if you're wondering what that means, don't worry, we'll cover it in the next video. But for now, just have a play around with sorting a data frame. You could even sort it by another value. Just don't save it in place. Just see what it does. You could change this into any column name that's a number. And you could change this to false if you wanted to and see if that works out. But otherwise, if you're following along, let's make some changes to df temp. Okay, now we've made a copy of our original data frame. We can start to edit df temp without any worries of damaging our original data. So if we ever needed to revert back to it, we can, with no troubles at all. So what we're going to do in this video is we're going to take these dates. We're going to use Pandas datetime as well as some Pandas datetime attributes to enrich our data set. And if you're wondering, what is Daniel talking about, enrich our data set? Well, this little practice that we're about to dive into is called feature engineering. If you remember, right back up in step 4, well, we've covered a lot already. We've got a whole bunch of features, and these are all listed here. What feature engineering means is either creating a new feature, so something like usage band, maybe completely different to usage band, but we would just add it on here, and then there could be a description, or we would dive into one of these and go sale date, and we change it around a little bit. So that's the process of feature engineering. So let's do that, but with the dates. Now, how can we do that? Well, first of all, we're going to see it in action, then we're going to discuss what's happening. This is something you might want to do for almost any time series project you're working on. So let's make a little heading here, add date time parameters for sale date column. Wonderful. And Pandas has a beautiful little Pandas date time. Oh, I just did Pandas data. I'm getting trigger happy. Date time attributes. This is what we're going to be using, right? We've turned our sale date column into a date time index. See there? Immutable ND array of datetime data. What we can do now is access some attributes of that date. And this is what I mean here. So we can go year, the year of that datetime, the month, the day, the hour, the minute, the second, the microsecond, the nanosecond, far out. That's getting pretty deep. Is it the start of a month? Is it the end of a month? Is it the start of a quarter? Now I want you to think about, why might this value, these features be valuable? Just without even seeing it, without even coding it up, if you're making a sale, why would it be a good idea to maybe know whether or not it was the end of a quarter or the start of a quarter or the start of a month or something like that? Why would it be? Now, it's okay if you're unsure, but this is part of being a data scientist or a machine learning engineer, right? It's about knowing a little bit about everything. So if you're working on time series sales, maybe it's a good idea to know whether it's the start of a quarter, because sales might be increasing because it's the start of a quarter. Or maybe it's the end of a quarter and sales are going down because everyone's tight on budget. And maybe if it's the start of the year, no one wants to buy anything, but it's the end of the year and people are like, oh yes, let's use the rest of our budget. Let's buy heaps of things. You don't have to know in-depth knowledge. This is just one thing you can do to enrich your date time objects. So let's go in here. How can we do this? We can add a column. What we're going to do is add a datetime parameter for the sale date column on the end of our df temp. And now again, talking about it isn't as good as having a look. So we'll go sale year. And how would we do this? So what we're doing here is we're making a column df temp sale year equals df temp sale date. So this means we're accessing the sale date column. And then we can access the datetime part of sale date by using dt. So dt for datetime. And then we can access the year attribute by putting .year. So let's have a look at this. What does this tell us? Datetime index.year, the year of the datetime. Before we even reassign a column, let's just take the first row and see what this does. 1989. Okay, and let's do the same again, but let's do it with day. Okay, 17th. All right, and now if we just did it with nothing, so if we just did the sale date, Ah, there we go. So we see that that's accessed the year, that's accessed the day. So let's enrich our data frame with a few columns pertaining to these different values. And if you're not sure what I mean, let's see it in action. If in doubt, run the code. Sale year equals that. And then what we might do is we might just do month, day, day of week, day of year. And of course we could do more, but in the essence of time, really we could make a function that does basically all of these. But what we're going to do is just do 5 or 6 to demonstrate. So let's do that. We could copy it, but we're going to practice coding it out. So we go here, sale month equals df temp.saledate, tab autocomplete, d month, and df temp sale day equals df temp.saledate, dt day, df temp, and we're going to go sale day of week. That was one we said. Day of week. Can you read that? Maybe we do camel case. Beautiful. Equals df temp.saledate.dt.day of week. Df temp sale day of year equals df temp. Now, as you can see, there's a lot of redundant code here. There might be a function in there somewhere. That's a good challenge for you, is to see if you can functionize this and maybe even go to the Pandas documentation and add a few more different parameters to it to enrich our data set. And now, what do you think that this might do? Well, let's have a look. We'll run that, and then we'll go here, df temp. We're going to view the head, and we'll transpose it so we can see all the columns. Let's go right down the bottom. Ah, there we go. So what we've done is we've created, so see here, sale year, sale month, sale day of week, sale day of year. We've created these 5 columns. And what it's done is it's just taken the sale date and extracted some of those values and added them as more features on the back end of our data frame. Now, of course, these features won't be listed in our data dictionary, but if we were to go in and share this with someone else, maybe that would be something we add to the data dictionary, but we won't do that for now. And so with this information here, we probably don't need the sale date column anymore. This one here, probably a bit excess now. So what we might do is remove that. So let's drop it. So we'll put in here, little comment. Now we've enriched our data frame. And remember, because we're working on df temp, if we ever needed the sale date column back, we could just go back to our df, our original data frame that we imported. Now I've enriched our data frame with date time features. We can remove sale date. So let's go df temp dot drop, and we're going to go sale date on axis equals 1, in place equals true. Remember, in place happens in place, so we don't have to go df temp equals. Wonderful. Now, if we try to do this, we're going to get an error because sale date doesn't exist anymore, but that is okay because we've got the information. It's just now across 5 different columns. Boom, 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 boom. And if we ever wanted it back, we can go back to our original data frame. Now, I also like to check the values of different columns. Now, this is all about EDA, right? And exploratory data analysis is just really checking out what's happening. So what we might do is let's pick one. What do we got here? How about state, US state in which sale occurred? I wonder which state has the most sales. If you're from the US, whatever state you're in, do you reckon you've made the most sales? Let's have a look. Value counts. Maybe it's going to be Wyoming. No. Florida, Texas. So a lot of sales are happening. Wow. Okay. So Washington. Does Wyoming even have a single sale? I can't see it in that list. Maybe you can. Oh, there we go. Wyoming. Woo! 1,672. Okay, so this is another part of EDA. You could check more columns if you want. You could go through and check different value counts. Remember, value counts is really handy. This is, you're just looking at the spread of data. That's another way of looking at the distribution. I'm a bit tired of exploring the data. Let's do modeling. Yeah, let's do that. That's way more fun, building machine learning model. So we've done enough EDA. we could always do more, but let's start to do some model-driven EDA. Now, what is model-driven EDA? Well, because there's so many features here, we could spend all day just going through each of these columns, finding the value counts, doing a distribution plot, making more plots, but at the end of the day, we kind of know what our evaluation metric is, so why don't we try and just head towards that, seeing if we can? Well, how would we build a model? Let's build a machine learning model, but remember, what are we trying to do? Well, if we come back, let's check data frame. We're trying to use all of the independent variables to predict sale price. All right, so that means if we just drop all the columns, drop sale price, that should be our X. And then if we use sale price, the column itself, that should be our Y. But what kind of machine learning model do we use? Well, remember, we've got Scikit-Learn machine learning map. If we go here, choosing the right estimator, and this is our old faithful. So if we were to start here, if we go through this, do we have above 50 samples? Yes. Are we predicting a category? No. Predicting a quantity? Yes, we are predicting a number. We are doing a regression problem. Now, if we were to follow this through, we've got a bunch of different model options here in the green, but because we already had some experience with random forest, a random forest classifier that is, what we might do is check out its counterpart, the random forest regressor. So if we were to go through here, forest of randomized trees, there's a classifier, and there's random forest regressor. All right, well, let's see what we can do. We've seen this before with Scikit-Learn of how to import a model. So if we go from sklearn.ensemble, and remember, if you want to see exactly how to do this, you could just go into here, random forest regressor, and it'll tell you what to do. There might even be an example down here. There we go, from sklearn.ensemble import random forest regressor. That's what we're going to do. Import random forest regressor. Oh, this is exciting. We're getting into modeling already. We'll instantiate a model. So model equals random forest regressor. And we're going to set the number of jobs to equal -1. What does this mean? Well, that means it's going to use as many cores as possible on my computer. Because we're dealing with, how many rows are we dealing with? df temp. We want the len. We're dealing with 412,000 rows. So that means our machine learning model has to go through 412,000 plus rows of this, try to work out all the patterns between these columns, and then try and calculate sale price. That's a lot. And what we might also do from now on is, remember how we used to set, we could do this, NP random seed 42. We could set that in all of our cells. But another way to do it is with our models, there's a parameter called random state. We can go equals 42. And remember to check the documentation of what's going on. Oh, have we not, I can't press Shift Tab for some reason. I'll just go to the documentation here. We'll see what random state means. Here we go. Controls both the randomness of the bootstrapping of the samples when used when building trees if bootstrap equals true, and the sampling of the features to consider. Okay, so long story short, this is going to, it acts like NP random seed. And if we go here, n jobs, there we go. None means 1 unless job lib. -1 means using all processes. So these are the two that we're setting, right? Wonderful. And so to fit it, we would go fit, and we need to drop the sale price column. So this is our X. So sale price and axis equals 1. So we're dropping sale price. And then we're going to pass it just the sale price column as the target. So this is model.fit, this is X, and this is Y. So df temp sale price. Let's see if it works. Oh no, we got a value error. What's it saying? Could not convert string to float low. You know why this is? It's because if we go df.info, all of our data is not in numeric format. Int, float, int, object, usage band. Okay, what What type is that? Let's have a look. This is part of model-driven EDA, right? Our machine learning model just told us that. Thanks to the beautiful people of Scikit-Learn, they've put in these errors to help us out of what's going on. So usage, no, not user warning, usage band dot D type. Hold on, what's going on there? D type O, object. Okay, so maybe it's a string or something like that. And the other thing is, I just remembered, we've got a whole bunch of missing values. So from what we know about our machine learning models, we're trying to get into modeling, but we've got data that's not numeric and a whole bunch of data that's missing. So before we build a machine learning model, we'll have to take care of that. So that's probably what we'll do over the next couple of videos. We'll do some model-driven EDA. And the beautiful thing is we just tried to run that machine learning model and it told us, hey, we can't, it's not going to work because you've got non-numbers in your data. You've got some strings in your data. And if we were to go again, it might tell us eventually that we've got missing data. So that's what we need to handle first. Well, we're making good progress on this bulldozer price regression problem. In the last video, we tried to build a machine learning model. We learned that we've got some data that isn't in numeric format. So see here, we've got some strings. And if we check df, oh, actually, we're working with df temp. My bad. See, these are things that you're going to forget, that you're going to go through, that you're going to mix up. So df temp, still same problem, right? Because we've got some values here, some columns that are numeric and a whole bunch that aren't. So what can we do about that? Well, oh, not even, Daniel, what are you doing? You're not even working with your temporary data frame. Okay. Well, this is all part of the game, right? Making mistakes and then going back and fixing them. That's part of being a data scientist, heaps of experimentation. So one way we can turn all of our string data or non-numeric data into numbers is by converting them into Pandas categories. So that's, oh, what's that mean? So convert strings to categories. Now we'll put it here. One way we can turn all of our data into numbers is by converting them into Pandas categories. So like the date time object that we saw when we imported sale date, Pandas has another data type called category. Let's have a look at the Pandas types API. Oh, there we go. This is probably a bit better. We can see this here. So pandas.api.types. Where can we have a look at this? Utility functions, data types, related functionality. So here we go. Let's copy this, but let's just read it out first. What's going on here? D-type introspection. So D-types is bool type, is categorical type. Okay, pandas D-type. Convert input into a pandas only D-type object or NumPy data type object. Okay, so we've got a fair few options here to have a look at different data types with pandas. But since we're focusing on converting strings to categories, let's see how we do that. Let's put a little link here. We can check the different data types compatible with pandas here. So remember, a lot of machine learning is basically getting some data, what we got here, and then preparing it to run with an existing machine learning model that we've chosen from our machine learning map isn't here. So it's about getting some inputs, aka a whole bunch of data that we've got here, all this sort of stuff here, and then massaging it, or essentially, yeah, that's a good word for it, massaging it into a way that it works with a machine learning model. So that machine learning model can find the patterns. Someone else has built this model for us, and we're going to thank them very much. And then it's going to find the patterns and give us some outputs, aka some predictions, some patterns, some labels, something like that. And then we can evaluate how well that works. This is what we're doing here. We're manipulating our inputs to work with our machine learning model. So let's have a look. Let's remind ourselves, df-temp.head of what we're working with. Okay, yep, we've seen this a fair few times. This is just another way to look at it. Always a good idea to look at your data. And so what we might do is try to use one of these API types. So what can we use? Is there a string one here? There we go. API types is string D type. How do we use this? Is string D type string. Okay. Let's try this out. So pd.api.types is string dtype dftemp usage band. User warning. Why is there a user warning? Is there not a user warning column? I don't know. Who knows? I'm going to keep making that mistake, but let's check. Okay, so it is a string. The usage band column is a string. Now we could do the same thing for almost every other column, but why would we go through and write that much code? Let's build a little for loop that does it for us. So find the columns which contain strings. Because if we know which columns contain strings, then we can convert them into some kind of number and our machine learning model will be happy. So for label columns in dftemp, now I'm going to go through this one first and then we'll retrospect it afterwards because you might be looking at this going, oh, I don't know what dftemp.items is, but maybe you want to try it out. Maybe you want to pause the video and try it out and you explain it to me. Now, types, and if not, that's all right. We're going to go through it. dtype. Now all we're doing is we're just copying something like this because we're trying to find all the columns with strings. And we're going to pass this, or actually, this is more content. That's what the documentation says. And we're going to pass content here. So does this make sense? You don't know what dftemp.items does unless you've checked it, but we're going to go for label content, and then we're going to check if the content is a string data type. Yes. Then we're going to print the label. Now you might be able to guess what this does, but if not, that's okay. We're going to see what it does anyway. If in doubt, run the code. And we got here. Okay, so these are all the columns that are string data types. Does that make sense? If you're wondering what dftemp items does, it treats our data frame like a dictionary, which is kind of what it is, right? It's a dictionary of keys and values. Okay, the keys are the column names and the values are what you see in the column. So let's give a little example. If you're wondering what df.items does, here's an example. So we'll create a random dictionary equals, let's be creative, key 1 equals hello and key 2 equals world. Maybe you can be a little bit more creative than me, but we're going to go for key value in random dict.items. So see how we've got just .items? Same with up here. .items. We're going to go, we want print f, this is a key, and then we'll pass it key. And then we'll also go f, this is a value. Value. Wonderful. So if you've worked with Python dictionaries before, you might be able to tell what's going to happen here. Oh, what have we got here? Oh, I see. It's printed it out twice. That's all right. We can kind of get what's going on there. So essentially, what happens here is for label.content is basically labels are the column names and the content is the content of the column. So this is what this is doing. This brilliant little for loop tells us all the columns that contains the string data type. Wonderful. So now that we know that, what can we do? Well, if we were to read through our Pandas data types related functionality, right, we're not going to do that, but it's somewhere in here or somewhere in there. Or you could also search up how to change the data type of a Pandas column. One of the things you might stumble across with is converting strings into categories. Rather than talk about it, Daniel, come on, let's just code it. Let's see it happen. All right. Let's do it. So this will turn all of the string values into category values. And you're wondering, why would we do this? Well, it's going to make a lot of sense in a second. So for label, we're going to just bring the same for loop that we wrote up before, dftemp.items. And we're going to go if the pd.api, this is a fairly long one, types is string dtype. That's a mouthful. So basically is the content a string. If true, we want to dftemp, we want to change that column. So see here, the column name. So we want to access that column name. We want to set it equal to the content. So right, keep the column name, but change the content to as type category. I need to spell this right, .cat as ordered. Oh my goodness. What is happening here? Well, let's have a look. What is going to happen? This might take a little while because we've got to go through a lot of columns. But we're going to preload our next Jupyter cell, right? Because we're pumping through this. Beautiful. df.temp.info. Have a look here. What is going on? What have we changed? I'll give you a hint. It's something over here. Well, it is this. So now these used to be objects, aka they used to be strings. Now we've changed them into categories. Well, that's interesting. What does this mean? Well, this is where we can have a look. Remember, we're trying to make sure all of our data frame is numeric. So we can't pass strings to a machine learning model. So this is what we're working towards. So df.temp. Let's check out, which one did we check before? Was it the state? Beautiful. Let's check that. So df.temp.state.cat categories. Wonderful. There's Old Faithful, Wyoming. Shout out to Wyoming and every other state, wherever you're from. And every other country, to be honest, because this is on the internet. All right, so we have categories here. And what this is going to do is, remember when we did df.state.valueCounts? Remember when we did this? So if we were to go through all of these, because remember how we did up here? There's a fair few things we've just covered here. Daniel, come on, explain them. As ordered means these are now ordered. See how they're alphabetical? A, C, B. Oh, wait, there's no B. These aren't ordered here. Well, they're ordered by their value counts. But essentially what this has done is it turned it from strings to categories. So this is going to assign, when we called this, it's going to assign a numerical value to each category. So now looking at this, it doesn't really make sense, right? Because these still look like strings. However, under the hood, Pandas is treating these as numbers. So Alabama might be 1, Alaska might be 2, Arizona might be 3. And we can check that by going df.temp.state.cat for category. So we're accessing the cat. Remember how we access the date time using DT? Well, now we're accessing the category .codes. Okay. So now we have a way that our data frame can be accessed. At least all the string values, right, have been now converted to categories. Because see here, we looped through our data frame and we figured out whether they're a string or not. And we've changed their data type to categories and we've given them order. So now we have all these categories here and we have a way to access their numeric value. Whew. Not bad, hey? I'm rubbing my hands together. You might not be able to hear that because I'm really excited. But even though we have a way to access our data as numeric, we still have a whole bunch of missing values. So let's write this down. Let's give some thanks. So thanks to Pandas categories, we now have a way to access all of our data in the form of numbers. Beautiful. But we still have a bunch of missing data. Let's have a look at that. Check missing data. So we got df.temp.isNull.sum. Now let's get some ratios here, right? So let's divide it by the length of the data frame. So we've got no missing values in these columns here because these are all zeros. And then we have, okay, so not much missing there, but usage band has 80% of missing data, 85% missing data, 81% missing data, 52%. So, 93, my goodness. Maybe something's going on there. We'd probably have to, if this was a data set in the wild we were working on with a client, maybe we'd ask them. But since it's from Kaggle, accessing a subject matter expert is probably pretty hard on this data set. So these are some things we might explore a bit more, but we're on our mission to build a machine learning model. So what we might have to do next is fill these missing values. But before we do that, since we've made some changes on our df.temp, we'll save it to a new CSV so we can, if we were to just start this notebook from fresh, we can just import our manipulated data frame and start exactly where we are now. So save preprocessed data, and we'll go export current temp data frame. So we'll go dftemp.toCSV. We'll put it back in the data folder. So blue book for bulldozers, and we're going to call it just something simple like traintemp.csv. Beautiful. We want to index equals false, otherwise we'll come up with some funny things when we re-import it. And then we're going to import pre-processed data. And now you could do this for whatever stage you're at, right? If you've made some changes to the temporary data frame, I just decided to do it now because it crossed my mind. You can do it whatever stage you're at. If you've updated some columns, if you've done some feature engineering, you can export it and re-import it. That way, if you're coming back at a later session, you don't have to make those changes again. You don't have to run your notebook from the top. You could just run it from here. Oh no, we've just written it to file. Daniel, come on, we want to read it now. pd.readcsv. This should work. This should re-import it. And then if we went dftemp.head, we should have the exact same data frame that we're working with now. Wonderful. And so again, we'll just remind ourselves that we have a lot of missing values to deal with. Beautiful. Just because we exported and re-imported our data frame doesn't mean that our missing values have been handled. So that's probably what we're going to do. Well, it is what we're going to do in the next video as we work towards getting our data ready for a machine learning model. Let's start to fill some missing values. All right, let's fill some of those missing values, shall we? So we'll make a little heading here. Fill missing values. Beautiful. And we got a fair few missing values here. So what we might do, I think we'll do the numeric missing values first. So let's put it here. So another little heading. And we'll go, let's change this to number 2. Just because I like the aesthetic, and we'll go fill numeric missing values first. Wonderful. Now, how do we check what columns are numeric and what columns aren't numeric? So what we might do, remember the is string D type? We did that before. We looped through our data frame right up here. Oh, we could probably press Shift Enter there. Where is it? So is string D type. So there's another one. As you might have guessed, there's also is numeric data type. Is it up here? No, might be here. So if we go here, is numeric. There we go. Check whether the provided array or D type is of numeric D type. Because we want to fill numeric data, we want to find out which columns are numeric. Let's loop through. For label content in dftemp.items. So we're going to loop through the column names as well as what each column contains. And we're going to if api.types.is numeric dtype. Does that make sense? What do we need to put in here? If the content, yes. If the content in the column is numeric, we want to print out the label. So that's going to be the name of the column. Wonderful. So let's check out one of these. We made these ones down here, so we know that they're numeric. But let's check out, just for fun, model ID. Wonderful. So this is going to be the model ID. Or actually, we can check what that is. Model ID, identifier for your unique machine model, i.e. FI model description. Beautiful. Okay, so these are our numeric types. And now what we might do is find out which ones of these have missing values. We're more focused on it at the moment. We want to fill the missing numeric columns with some sort of value. Check for which numeric columns have null values. Now, how might we do this? Well, first of all, let's start it out with for label content. We'll just write exactly what we did before. dftemp.items. And now we want to go if pd.api.types.is numeric. I tried to do tab, but there was too many options. Is numeric dtype content. Wonderful. And then what we might need to do is check. There's a feature or a function in Pandas called isNull. So if we go pd isNull, Pandas isNull, here we go. So this detects missing values for an array-like object. So we can do this by Pandas isNull content, that's what we want. So we'll do another if statement here. So pd isNull, so this is going to go, is there null values in the content, aka the column? In the whole column, is there null values? But we need to make sure there's a sum, so total. So if there's any null values, so if this is higher than 0, we want to print the label. This should tell us which columns have null values. All right, now that we know which columns or which numeric columns have null values, we can fill them with something. So what we might do is fill the numeric rows with the median. So how might we do that? We can just take this. We'll copy this down here. Right, we're going to go fill numeric rows with the median. Wonderful, but there's one other thing that we have to actually do. We go here, well, you don't have to do it, but we're going to do it anyway. And I'm going to write it out first, because we're going to add a binary column, which tells us if the data was missing or not. That comment's a bit long, but that doesn't matter. Why do you think we might do this? I'll just let you have a think about it while we do it. We'll go here, is missing equals pd isNull content. Wonderful. And then what we're going to do here is fill missing numeric values with median. df temp label equals content dot fill in a content dot median. Whew. We only built upon what we've done before, but we added 2 new steps in here. Before we hit shift and enter on this, we're going against our rule, if in doubt run the code. I want you to just think why we might put this column here. You might be asking as well, why are we filling it with the median? Why not the mean? Well, the reason why we're adding this column here is because if we just fill up all of our missing data with the median, then there might be a reason for that missing value that was there. We're keeping that information, the fact that that variable was missing, by adding a column which is true or false if it was missing or not. So that means if we find a row that has a missing auctioneer ID value, and then we fill it with the median of the auction ID column, there's going to be a column on the very end of our data frame which says true, which is basically 0 or 1, which tells us that, hey, we filled up this auctioneer ID row, but originally that column or this row was missing this value. We're keeping that data, we're keeping that information, that the fact that that particular sample had a missing auctioneer ID in the data set. So we're keeping that information there, but then we're filling it up with the median. And you might be asking, why the median, right? Why not the mean? Well, the thing here, the reason being is because median is more robust than the mean. And you might be wondering, what do you mean that median is more robust than the mean? Well, the thing is, when you use the mean, when we have a lot of different values, so we have 412,000 values. The mean of a lot of different values can be very sensitive to outliers. So let me demonstrate it with a kind of a rough example. So demonstrate how median is more robust than mean. And we've just run this cell, so we'll check out what happened with that in a second. I just want to give you an example of why we might use the median. You might want to search for this, go, why use median over mean? That could be some sort of extension. You could do some research there. But we go here. We go tens equals np full. What this is going to do, we're creating an array, 1,000 long, with a value of 100. So say there's 1,000 people. Why are we calling it this tens? So 100. Hundreds, there's 1,000 people, each with $100 each. Okay, and then we'll make one with hundreds and a billion. Let's say out of those 1,000 people, Bill Gates just walked in and he's got $1 billion in his pocket. So we'll go, not tens, we want hundreds. So there's 1,000 people with $100, but now Bill Gates has walked in and he has $1 billion. That's 9 zeros. My goodness, that's a lot of zeros. 1, 2, 3, 1, 2, 3, 1, 2, 3. Well done. Okay. So what we're going to do here is go MP mean hundreds, and then we're going to go MP mean hundreds billion, and then we're going to go MP median hundreds, and then we're going to go NP median hundreds billion. So all we're doing is we're taking the mean and the mean of each of these and the median of each of these. Let's see. Whoa. So see what I mean here? In our array, hundreds, let's have a look at it. This is just 1,000 examples of the number 100. The mean is 100. That makes sense. And the median is also 100. But when we add 1 billion to the end, it should be right down here somewhere, or maybe it's not. It's in hundreds billion. When we add one example of 1 billion being right at the end, look how much that influences our mean. And now this is an extreme example, right? We're using 1 billion versus 100, so we got a couple of orders of magnitude here. Look how different it is to the median. In its purest form, this is why we're using the median. And so you might come across that in your research of why using median to the mean. But the main reason is because the median is more robust to outliers. But with that being covered, let's have a look at what we just did. What did we just do with this? So to figure that out, what we can do now is check if there's any null numeric values. And how did we do that before? Well, we did for label content and dftemp.items. That's what we're after. Yep. If pd.api.is, oh no, types.is, I'm getting ahead of myself here. Numeric dtype content, wonderful. If pd is null, content.sum, print label. So this should tell us if there is still any numeric values or numeric columns that have null values in it, it should print out those column names. And it prints out nothing. The reason being is because we just filled the content, the ones which were missing, with the median. Now let's check to see what our binary column did. Okay, check to see. So if this worked, we should have, let's go up here. How many auctioneer ID values were missing? Can we find that out from our previous one? Auctioneer ID. Okay, so we should have the fact that we've filled up. False should be the total number of rows minus this. So the true should be this value of our binary column, right? Because it wasn't missing. So let's go here. Oh no, true should be this number, because that's how many missing values there were. See there? So what we've done here, before we filled our values, we've checked to see how many missing values there are. So our binary column should be true for 20,136 examples, because that's how many examples we've filled. So let's check that out. So df_temp dot, because we've created a column, auctioneer ID is missing. See here, we've got label plus is missing. Now this should be true and false. Beautiful. What that means is that we filled up 20,136 values in the auctioneer ID column, not the is missing column, because remember we just made this, with the median of the original auction idea column. Whew. Now, that was pretty full on, but we've still got some missing values in our data frame. Let's check out what else do we have. We filled up all the numeric missing values, but we've still got some of these. We still got a fair few. All these ones are 0. They don't have any missing values, so that's good. They're getting ready to use with our machine learning model, but we still have to fill all of these before we can use our data with a machine learning model. So let's do that in the next video. Now we filled up all the missing numerical values in our data frame. Let's do the same, but for the rest of the missing values, which are these ones here with numbers. So we found this out using dftemp.isna.sum. So we've got a fair few that are still missing. And I have a hunch that they're all categorical. Remember how we found columns before that with a string data type? Let's do that again, but this time, because we've filled up all the numeric data, let's find all the columns that aren't numeric data. And that should tell us all of these columns that still have missing values. Does that make sense? So because we've filled up all of the columns with numeric data, we want to find the columns that aren't numeric data. So make a little heading here. So filling and turning categorical variables into numbers. We're working on categorical variables now because we've already worked on our numerical variables. So let's go check for columns which aren't numeric. And we'll go for label content in df temp dot items. And then we'll go if not pd dot api dot types dot is numeric. So does this make sense? If not, so if they're not numeric, because we filled up all the variables which are numeric, now we want to find the ones which aren't numeric. Content, and then we want to go print label. Beautiful. Now this is going to tell us all of the values, all of the columns that aren't numeric, but some of them, okay, usage band. That has a fair few missing values. So that has 339,000 missing values. So now we know all of the columns that aren't numeric. What can we do? How would we fill these up? When we turned a string column into categories, we had access to an attribute called codes, which gave us a numerical value for all of the variables in that column. Let's have a look at an example before we do it. So PD categorical. So what this is going to do is go pandas categorical type, and then we're going to pass it df temp state. We'll look at the state column because that's the one we used an example before. And we'll see what this does. Categories. 53 objects. So this is categories. Okay. Can we do D type here? Categorical D type. Okay. Yeah. And what we might do is dot codes. Ah, okay. So this is how we turn all of the state, the variables in the state column, into numbers. So how would we do this for everything? All of the categorical columns, because that's what we need to do, right? We need to fill in the missing categorical variables and turn them into numbers at the same time. So we might use this. Let's keep that there. I'll make another cell here. We might go turn categorical variables into numbers and fill missing. So let's see, let's loop through for content in dftemp.items. And then if not, so if it's not, just like we've done up here, so if it's not a numerical type, pd.api.types.is numeric type. But remember, we've got the not here, so it's checking if it's not numeric D type. Content, wonderful. Because we know it's not numeric, we might check to see if it's missing again. And we're going to add a binary column, just like we did in the previous video with numerical data. So add a binary column to indicate whether sample had missing value. Wonderful. So dftemp, here we go, label plus, we'll do a little string here, is underscore missing equals pd is null content. So that's just going to return true or false if the value was missing. So if the categorical value is missing, it'll return true. It'll make a column and it'll assign that to true. If it's not missing, it'll just have false, aka true is 1, false is 0. Turn categories into numbers and add +1. Now you might be wondering, Daniel, why are we adding +1? Well, actually, let's write the line of code first, because let's see the code. PD categorical content.codes +1. Now, you might be wondering why we're doing +1 to all these codes. So if we did this, +1, see how it goes up? Keep that there. Goes up, okay? Why would we do this? Well, the way Pandas categories works is it automatically, if there was some missing value in here, it assigns that a code of -1. But we don't want that. We want it to be not -1, we want it to be 0. So maybe if we find a column that has missing values, we might be able to see this. If not, we go usage, oh no, is it usage band? That one has a lot of missing values, doesn't it? Usage band. Okay, let's have a look at this column. Dot codes. Oh, -1, -1, -1, beautiful. We don't want this to be -1, so we're going to add 1 there. So all of our numbers are positive in our data frame. That's the reason why we add +1 here. So if we were to do this, boom. That way we know when we turn our data frame, our numeric, into all numbers, all categories, that way we know 0 is actually missing. All the other categories are just +1 on what their category code is. So let's run this cell. This might take a little while. We have a fair few missing values, so we have to fill all of these. So what we're doing, we're turning all of these columns that are non-numeric. Remember, that's what we found here, non-numeric. We're taking those missing values, or actually first we're turning them into categories. If they have a missing value, that row will be assigned -1, but we're adding +1 to the code. So all the missing values are going to be 0. And all of the values that are still there, the categories, are going to be some number pertaining to whatever Pandas decided that their categories are. Oh, beautiful. It's worked. Okay. So now we can check to see what we've done by going dftemp.info. So we see here, okay, so now we have 103 different columns. Wow. Well, let's have a look. So if we go dftemp.head.t, okay. So see, these are all our categorical is missing columns that have been adjusted, that have been added on the end. Now this is from this line of code here. So see what I mean? Add a binary column to indicate whether sample had missing value. So this means that for sample 0, it had a differential type. It was missing. So if we went back and found that column for sample 0, it would be filled with a value 0 instead of just missing. Now, one last check is to see if there are any more missing values, because what we've done, filling up the numeric and categorical values of our data frame and turning them into numbers, there shouldn't be any more missing values. Beautiful. So these should be all zeros. So maybe, is that getting a bit cut off? 10. See what I mean? It's getting truncated. 20. Wonderful. So we've got no more missing values in our data frame, and our data should be all numeric. What is that telling you? What do you know about machine learning models? What do those 2 points hint to you when thinking about machine learning models? We'll wait to the next video so we can find out. So the beautiful thing is, now that our data has no missing values and is turned all into numeric values, we should be able to build a machine learning model. So let's do that. We've instantiated one way back up here as model, way back when we started the modeling section. Far out. We've covered a fair bit of ground here. You should be proud. Modeling, wonderful. We're going to do basically the exact same thing. So let's build a machine learning model. We could copy this, but we're just going to write it out again. We'll leave a bit of communication to ourselves. So now that all of our data is numeric, as well as our data frame has no missing values, we should be able to build a machine learning model. Wonderful. So remember what our goal is? It's to find patterns in the data to predict the sale price. So that's what we'll have to do. Let's have a look, dftemp.head, one last look at our data before we model it. So we need to drop the sale price column so that we can build a machine learning model that takes in all of the other columns except for sale price, finds the patterns, and then tries to predict sale price. So what I'm going to do, I'm going to set up a little timer magic. And if you haven't seen this before, the percentage sign, that's a Jupyter Notebook magic function. You can search up for a whole bunch of these, but what this is going to do is basically just calculate how much time this particular cell takes to run. And I'm going to do it on my computer, which is a MacBook Pro. How many rows do we have? We have 400,000 or something rows. This may take a little while. In previous examples, when we've worked with less data, our machine learning models have been pretty quick, right? Because it's only have to sort through a couple of hundred rows, but this is 412,000. I mean, of course, there are much bigger data sets, but we're starting to get up there, right? We're in the hundreds of thousands of samples. Instantiate model. So what this time thing is going to do is, because it's our goal as a data scientist, as a machine learning engineer, is to do as many experiments as fast as possible. If you're training models on all of the data all the time, it's going to take a fairly long time. So I'm just going to demonstrate how long it takes for my personal computer to use a baseline random forest regressor model to find all the patterns in all 412,000 rows. So don't worry, you're not going to have to sit there and watch it run. Once we kick it off, I'll pause the video and then come back and show you how long it took. The ways of thinking I want you to start thinking about is, when you're doing experiments, start to think to yourself, how can I reduce the amount of time it takes between my experiments? The reason being is because you're not always trying to do the right thing. You're trying to figure out what's wrong, what doesn't work. So that's the rationale between trying to speed up your time between experiments. And as I type that, as I talk, what we're doing here is we're just instantiating a random forest model. We're going to put random state equals to 42 there. Random state equals 42. That way our results will be reproducible. So this is all we're doing. We've imported the random forest regressor class because we're working on a regression problem. We're setting n jobs to equal -1 because this is a fairly large data set for what we've been working with for now. So I want to use all of the cores on my computer, and I want random state to equal 42 so our results are reproducible. And I'm going to fit the model to the data. So this is our X and this is our Y. Remember, we're trying to predict sale price based on all the other columns except for sale price. So when I kick this off, this will take a few minutes, but I'm going to pause the video, and because we've got the little magic function time here, we can see how long it takes. So get ready to time travel in 3, 2, 1. All right, we're back. That was pretty quick, hey? So our model is finished, and it says here that the wall time was 6 minutes and 58 seconds. So it took about 7 minutes to go through 412,700 rows, which is actually pretty good, right? Think about how quickly you could look at that. How long would it take you to go through 412,000 different examples? You didn't have to wait for that time because I sped it up, but if you were to run this on your computer, it may take longer, it may take less time, depending on what sort of computer you have. I'm running this on a 13-inch MacBook Pro, I think from about 2016 or something like that. I'm not even exactly sure how much computing power mine has, but it's a laptop, so maybe not as much as a desktop. Anyway, but you can imagine as these numbers of rows started to really get up high, this could start to take a long time. If our goal as machine learning engineers, if our goal as data scientists is to reduce the amount of time between experiments, we're going to have to be pretty nifty when we try out different models, when we work on different data, because waiting 7 minutes every time, even if this number was higher, for a cell to run, that's going to slow us down a fair bit. So we'll see a little trick soon of how we can improve this, but why don't we score the model? So see how our model did. If it's gone over 412,000 rows, surely it's found some patterns in here. So we're going to score it on just the exact same data that it was trained on. So we'll copy this. And now remember, for a regression algorithm, the default score value here is going to be return the coefficient of determination, which is the R squared. Now, if you need a refresher on what R squared is, you can go, what is coefficient of determination? But in other words, it's a score that can go up to 1. It's 0 if all your model does is predict the mean of the sale price column. And it can go to -infinity if your model is absolute terrible. So we're looking for a value that's close to 1. So again, this might take a little while because the model has to compute the score of how it did across 412,000 rows. Boom! 0.98. Wow! If the maximum is 0.987, so closer to 0.99, so if the maximum is 1.0, does that mean our random forest regressor has almost found a perfect pattern for predicting the sale price based on other columns in the data frame? Not so fast. I want you to think about, before we get into the next video where we're going to cover it, why is this metric not reliable? Right? So if we have a look here, we fitted the model on this data, and then we've evaluated it on the same data. Why doesn't this metric hold much water? Have a think about it. We'll talk about it in the next video. In the last video, we left off scoring our machine learning model that we fitted to the data after we just filled all the numerical values, filled all the categorical values, and turned all our data into numbers. Model worked, our data had no missing values, and it was all numeric. But we left off with the question, why isn't this metric reliable? Let's put that here, because that's worth highlighting. Because remember, always remember, fitting a machine learning model or evaluating a machine learning model is just as important as fitting one. And that's where we're up to now. Because we've just fit a machine learning model, we have to make sure that our results hold water, right? Because we don't want to be promising things that our model can't do. So question, why doesn't the above metric hold water? Hold water is an expression for why isn't the metric reliable? That's just a way of speaking. So why doesn't it hold water? Why isn't it reliable? Have you had a think about it? I'll show you a diagram. That may refresh your memory. If we come back to our keynote, you remember from right back at the beginning, the most important concept in machine learning, aka the 3 sets. So what we've done is we've trained a machine learning model on one data set. But then what have we done? We come back to the code, we fit the model on the data set, on some data, but then we've evaluated it on the exact same data. Okay. So if we come back here, essentially what we've done is, if we were thinking about this as being a university course, we've learned the course materials, but what we've done, instead of testing our model on the equivalent of like a final exam, aka a test data set, we've just evaluated our machine learning model on the exact same materials that it's learned on. You were in one class and you got given a book to read, and then at the exact same time, it's just like you're going to be tested with the questions directly from that book you're reading. Okay. But we are after our model's ability to generalize, and aka the ability for a machine learning model to perform well on data it hasn't seen before. That's what we're after. If we go back to Kaggle, there's a training data set which contains data through the end of 2011. There's a validation set, and there's a test set. So that's what we're after. We need to evaluate our model not on the data we've trained it on, which is this. We need to evaluate it on the test data. But before we do that, if you remember right back up the top, let's go right back up the top till we imported our first data frame. I said we'd revisit this, and now the time has come. So we go here. We imported train and valid.csv. Wonder why did we do that? Well, it's all going to become clear in this video. So we've got train and valid CSV, we got valid CSV, and we've got train CSV. Why don't we just import them separately? Well, I wanted to demonstrate what it's like creating your own validation set rather than someone else creating it for you with a time series data set, which is what we're working on. So this is a perfect playground for that. So if we read here, train CSV is the training set. So basically what we've been working on, and valid CSV is a validation set. The key point here is because it's a time series, the training data set has data up to the end of 2011, whereas the validation set has data between January 1, 2012 to April 30, 2012. So what we will do, to better evaluate our model, we need to split our data up into training and validation sets. So let's do that. Let's go here, splitting data into train validation sets, because that's what we're after now. We've got a model, we can build models now, but we need to, rather than just build better models, we need to make sure that what we're evaluating with makes sense. So let's check our data again, as we always do. So maybe we can use the year what was it called? Sale year. So df temp sale year. There we go. Okay, so maybe because our data frame is in order, yes, this is going to help us. When we imported our data frame, we ordered it in the order of the sale dates. So now, reading this to create our own validation set, we want to split our data. So all of the rows up to 2011, so the sale year is 2011, that can be in the training set. And then all of the rows in 2012 can be the validation set. We won't worry about the test set for now because that's in a separate data set. The reason why we're only working on train and valid CSV is because we imported the train and valid.csv at the start of the notebook, this file here. So we have to create our own validation data set. So let's do that. So we go df temp, let's check the sale year.value counts. There we go, 2012. So there's 11,573 samples in 2012. All right, so to split our data into training and validation, it should be as easy as going, okay, let's introspect the sale year column, and every column that's equal to 2012 will be a validation set for sale year and example, and every row that's not equal of sale year, that's not equal to 2012, will be in the training set. So let's stop talking about it, Daniel, and let's see the code. So split data into training and validation. And this is something that you might have to do with your own time series data, right? Because you're not always going to be given in a Kaggle format, right? When you're working with a client or working on a project, you're not always going to automatically have your data in train, valid, and test. These are things you're going to have to create for yourself. Looking at the sale column or looking at the time column, looking at the date column and figuring out how you can make your own training and validation set. So that is exactly why we imported them as one set to begin with, so we could practice making our own training and validation sets. And I feel like I'm saying the word set a lot, but that's important because we go back to our keynote. This is the most important concept in machine learning because whatever we train our model on, we want to make sure we're evaluating it on something else. So come here. So the validation set is every row in df temp where the sale year column equals 2012. Yes, that's correct. And the df training set is every row in df temp where the sale year column is not equal to 2012. Wonderful. And then we might go len df val and len df train. So all this is going to tell us is the length of these two data frames. Beautiful. So now we have a validation set which contains 11,573 rows and a training data set which contains 401,125 rows or samples, and they're split on date. Beautiful. We're ticking boxes here. We are ticking boxes here. So now what we might do is split data into X and Y. We've seen this before. And so that way we have an X training set and a Y training set and an X valid set and a Y valid set, which is our data and labels. So we'll have X train, Y train equals df. Now we're working with the training set here. Drop. We want to drop the sale price column on the first axis, aka just drop the column. And we're going to set it to df train, Y train is going to be equal to sale price. So see how I'm doing it with a comma here? I'm being a bit tricky by just doing it in one line. Beautiful. And we're going here, valid, Y valid, not sure. Df val dot drop sale price, just the same again, but this time with the validation set. Df val dot, this is actually going to be sale price. There we go. And now we'll have a little gaze, inspect our data just to make sure we haven't made a little error somewhere. These should all be comparable shapes to each other. Y valid dot shape. So we're just taking these data sets that we're creating here and we're finding out the shapes of them. Beautiful. So our training set is 401,000 rows, or about that, with 102 features, 102 columns. Our Y training is 401,000 rows And then validation is about 11,500 with the same amount of columns for X and no columns for Y because Y is just one column. Let's have a look. Another look. This is what we do. Make sure all of our data. Okay, so these are all sale price. Beautiful. Woo. Okay. So we've got our data into train and validation sets. We've taken care of 2 of the 3 most important things or most important sets. We'll have a look at the test set later, but this is what we've created, a training set and a validation set. It's time to keep building some more models. So we might end this video here. And we've got to figure out a way to evaluate our machine learning model. So we'll probably have a look at that in the next video. We've got our data now in X train, Y train, X validation, Y validation. But in a previous video, we evaluated our model using the score function. What does the score function use? It uses the coefficient of determination. But if we remember right back up the top, we'll go right back up the top just to check it out because we wrote this down. We know that the evaluation metric for this competition, so for this project that we're working on, is RMSLE, or in other words, root mean squared log error. That's not the same as coefficient of determination. And if you're wondering where we got this evaluation function from, it's from the Kaggle competition overview.evaluation, which we saw right at the start, but we'll just check that out again. Evaluation. So the evaluation metric for this competition is the RMSLE. We can Google that to see what it actually is. So let's go here. Root mean squared log error. What is the difference between? How do you interpret root mean squared log root error? Okay, so we got a fair few options there. So if you wanted to read further, these are something you can look up, but we're going to work through this in code. Let's go down. You might be wondering, we haven't seen or really mentioned root mean squared log error. That's a bit of a mouthful in itself. So what we might do, we're going to have to create our own evaluation function because if we come back to our keynote, so classification and regression metrics, we're working on a regression problem here. This is one of the slides from, I think it was the Scikit-Learn section. We got a mean absolute error, okay. Mean squared error, MSE, okay. Root mean squared error, but this is missing the log component. Let's see if we could get that in through Scikit-Learn. So we'll go back here. What we might do is build our own. So building an evaluation function. Now, this is something you may have to do depending on the project you're working on, right? So if we're working on this Kaggle competition and they say that for some reason we have to use this metric, who knows, the people who posted this challenge may require this. They may have decided this is their best evaluation metric. Depending on what project you're working on, you may have to find an evaluation function which suits your use case the best. And so what we're going to do is create evaluation function. Because we're going to be running multiple experiments, we want to be fitting multiple different machine learning models and evaluating them. That's why we're going to build it into a function so we can use this functionality multiple times without having to repeat ourselves because we're kind of lazy when it comes to writing all this code. You know, I just want to experiment more and more. Create evaluation function. The competition uses root mean squared log error, RMSLE. So we can go from sklearn.metrics. I can tell you Scikit-Learn, you could go to the sklearn evaluation metrics, but we can go through here. We can have a look at some evaluation metrics. Mean squared log error. Okay, so we might use that. Mean squared log error. But we're going to have to add our own little piece on it because this is not root mean squared log error. So what we might do is we might take this one and we can import that. Let's do that. So from sklearn.metrics, import mean squared log error. And for the hell of it, we'll do mean absolute error. You make predictions on all the examples and then you minus your predictions from your actual values and take the average. That's the mean absolute error. So how much on average is your prediction from the actual sale price? But mean squared log error is more to do with the ratio. And most oftentimes with regression problems, right? If you're like $10 off something, like so if we were $10 off this sale price prediction, wouldn't really matter. But if we were 10% off, that'll be pretty bad, right? We don't want to be more than 10% off. Whatever value, insert something, it could be 20%, it could be 30%, but that's kind of the difference between these two, right? Anytime you see absolute, think of it as being $10 off. And anytime you see like squared or some sort of log, or think of it like the ratio, so being like 10% off. That's when these two, you can really compare them to each other. But we've got a little bit more of that in the slide. You might want to take a screenshot of that. That is a pretty good one, but this will all be in the slides you can check out later. We want to create an evaluation function. We've got mean squared log error. So how would we turn that into root mean squared log error? So let's try it out. So maybe we go here. I don't want to type out root mean, nah, that's too much. RMSLE. Root mean squared log error, beautiful. And that can just take ytest and ypred. It's going to take the same inputs as my scikit-learn function. So see how this takes true, ypred. It could be ytrue, it could be ytest, doesn't really matter. Ytest, and then we go here. We'll leave a little doc string for ourselves. Calculates root mean squared log error between predictions and true labels. Wonderful. And then we might go return, just nice and simple. We can just use np square root of mean squared log error. We'll have to pass this to the test values and the predictions to mean squared log error. That's actually pretty easy. What we're doing here, we're taking the square root, so the root component of the mean squared log error, between predictions and true labels. Wonderful. So we've created our own evaluation function that lines up with Kaggle's requirements, the root mean squared log error. Okay, and we probably want to check a few more things, like we want to create an evaluation function to check a few things at the same time, so we don't have to keep calling something like this. So let's create function to evaluate model on a few different levels. So again, evaluation is just as important as building the actual model. So we'll go here, show scores model. So we'll pass it our model. We'll make some predictions on the training data. So model.predict. So we'll evaluate how our model did on the training data, xtrain. And then we'll evaluate how our model did on the validation data, model.predict. We'll pass it our x validation here. If our model is performing better on the validation data set, that's hinting at us that our model is overfitting. So between training and validation, generally, because our validation set only has 12,000 examples and we're not training our model on it, you'd want to see slightly worse metrics on the validation set than versus the training set. So we'll go scores equal, maybe we'll return a dictionary of some sort. Yeah, so training, MAE, aka mean absolute error. We're gonna go, can I tab autocomplete mean absolute error? Yes, I can. Ytrain, so remember, we're just comparing the Ytrain, so this is the training mean absolute error on the training labels versus the training predictions. Beautiful. We're gonna go valid MAE. So again, you'd expect this valid MAE to be slightly worse than the training. This is gonna be yvalid, and this is gonna be valpreds. And then we're gonna go training RMSLE for root mean squared error, and we can do this using our fancy little function that we've just created up here. This is exciting. We're writing our own evaluation functions. Maybe that's a pull request potential to Scikit-Learn. Wonder why they haven't got root mean squared log error. Maybe it's not that popular, or maybe you can just easily create it yourself like that. Is that correct? Ytrain, train preds? I'm talking too much. Don't talk in code, kids. No, I'm kidding. You can do whatever you want. Here we go. Here, RMSLE, except don't under-evaluate your machine learning models. That's the only thing you're not allowed to do. Everyone loves a good model, but everyone loves a well-evaluated machine learning model even more. And finally, for good measure, since we're here, Let's do the default score. Or maybe we just import that. That's probably a bit better. R2, is it R2 score? What is this? Why is this not working? Tab autocomplete is giving me some issues. So we got R2, oh, it's just, oh no, R2 score, yeah. Trust your instincts, Daniel, come on. R2 score. So that's all we're changing there. Rather than recomputing something, we'll just import it. Now this is a fairly decent function, not gonna lie. Takes care of a few things. Train preds, probably some redundancy we could fix, but that's all right. We're trying to experiment as fast as possible. You might be thinking, wow, our experiments are getting slowed down. But with your own practice, without having to listen to me talk and go through these sort of things, you'll be whizzing through experiments. No, that's wrong, isn't it? This needs to be val preds. Val preds. Beautiful, and we're gonna return the scores. Okay, so what have we done here? So we've built an evaluation function in line with what's required for this particular project. And in our case, it's root mean squared log error. I'm gonna go horse saying that if I keep doing it. And then we've created another little helper function that's gonna do a whole bunch of other metrics. It's gonna make some predictions using a model we pass it to. And then it's gonna compare those predictions on a whole bunch of different playing fields, on the mean absolute error, on the root mean squared log error, and on the coefficient of determination. Whew. So that's probably enough for this one video, building our own custom evaluation functions. Now again, this is something you might want to do for your own projects. Because we're running as many experiments as possible, it is helpful to have evaluation functions like this so you can quickly do a whole bunch of different things rather than having to retype out this every time we try a new model. But let's press Shift and Enter in that so our functions are instantiated, and we're going to try and test them out in the next video. All right, so now we've got our own custom evaluation functions. We can evaluate how our model is doing. So the next logical step would be to train another one on the training data set and then evaluate it on the validation data set, or just using this beautiful function that we've crafted. Not so fast. Let's see why. So testing our model, this section is going to be, we're going to do it on a subset. So testing our model on a subset. Now this is mostly to tune the hyperparameters, because remember what we've been stressing, we want to decrease the amount of time it takes us between experiments. And if we come back up, remember how we time traveled in a previous video? And that took 6 minutes 58 seconds to fit a model on all those data, so on 400,000 rows. We don't have enough time to do that again. We can only time travel every so often. And so if we were to just write it out again, if we would instantiate our model, so model equals random forest regressor, n jobs equals -1 and a random state of 42. Wonderful. And then if we just did model.fit xtrain, I need to be careful here not to be trigger happy. If we did this, right, if we put a little time up here, time, that's going to take far too long, right? So we might put a note here. This takes far too long for experimenting, because that's going to take about 5 minutes. That's not what we're after. And again, if you have run this cell before, actually I probably should have told you this earlier. If you did run this cell on your computer and it's taking far too long for it to load, remember, you can always press the stop button up here. So if we run this, oh, well, that's too fast. That runs too fast. But if your cell is running, remember how there's a little star here? I'll show you. There'll be a star. Well, that happens too quick for this. You're going to have to trust me on this one. When you run a cell, this will turn into a star if it's running. You can stop it by pressing this button with that cell highlighted, and that'll stop that cell. So we'll come back. Let's not run that. We'll make sure we can't. So we comment it out. Beautiful. Because why? Because our data frame is 400,000 rows. There. And my little MacBook Pro has already calculated a lot of patterns in 400,000 rows, and it's like, well, I'm going to take a while, so you need to be patient with me. Well, that's fair enough, because I would take far longer than my MacBook Pro does to calculate through 400,000 rows. So, what our solution is to speed up our time between experiments, and that's what we're doing, testing our model on a subset. We could do something like this. Could just copy this, model.fit, Maybe we want to only do it on 10,000 rows. But there's an even better way, and it's right built into, we could do that, right? That's going to test it on 10,000 rows. But nah, there's a better way to do it. That is one option, so keep that in mind, that you can just slice your training data set. But the beautiful thing about random forests, and this is why we're focusing on it so much, is that they have this little feature in it called max samples. So change max samples value. All right, and if we wanted to figure out what max samples does, where would you go? Well, one option is if we go model equals random forest regressor. We're going to have heaps of practice instantiating these models. This is what it's about though, right? It's just about almost making this second nature of what it's like to just get a model instantiated, get it ready. Random state equals 42. There's our model. So that could be one option. But if we press Shift Tab here, we'll see the doc string, max features, max samples. Max samples, boom. Now if we come down here, let's find it. Max samples. There we go. If bootstrap is true, the number of samples to draw from X to train each base estimator. What does this mean? So if we go model, okay, bootstrap equals true, yes. And now each estimator sees max samples. Now where's max samples? None. So what does it mean? If none, it's going to be all, isn't it? Let's have a look. This is one I want you to have some practice doing, right? Is if you're not sure on something, it's looking it up and reading it in the docs. If bootstrap is true, the number of samples to draw from X, okay, so X is what we pass the model. If none, then draw X.shape samples, so it's going to draw them all. Now, if int, then draw max samples. So, what this means is that if we go xtrain.shape, 0. So if we leave max samples as none, every estimator, and in our case there's 100 because the default n estimators in random forest regressor is 100. So you can imagine n estimator as a small model. So each small model, so 100 small models are going to see every single one of these. So that's a large number, right? So this is all the calculations that we have to make, probably more than this, but this is what you can imagine. But instead, if we set max samples to something else, so say for example, maybe we only wanted to try 10,000 examples instead of 400,000, right? So closer to the shape of our validation set. We could change max samples set to 10,000. So this means that instead of looking at 400,000 rows, every estimator, so the 100 estimators for n estimators, we could also change this to be honest, but we'll leave it as default just for this example. So that means because we changed it to 10,000 times 100. Wow. So let's have a look here. Let's divide these two. How many times less? What do we got here? What number is that? How many zeros is there? 1,000,000. That's 1,000,000. I can count. 40 times less. So 40 times less data to compute on. So that means we should see a speed increase of 40x, or about that, right? Because it's not going to be perfect. So let's go here, change what we might do. Yep, that looks good. And then we'll create a new cell here. We'll leave our little time here because this is what we want to practice. So cutting down on the max number of samples each estimator can see improves, this is our hypothesis, improves training time. And let's have a look, model.fit. We'll do it on our training data now. So this shouldn't take too long. Maybe we might even have time to wait for it. Still might take a few seconds. This might be another opportunity to time travel. Oh, we didn't need to time travel much. Look at that. Wall time, 16 seconds instead of 7 minutes. Now that's a bit better, right? Now that's something that we can potentially just sit here and wait for. If you're doing 7-minute experiments all the time, or even longer if you had more data, you're going to lose patience, you're going to get distracted. But if we can keep our experiments like somewhere around 10 seconds, so that's pretty good, right? I can wait 10 seconds. And now the beauty comes in here when we can call our show scores function. So let's see what happens when we go show scores. Hopefully this works because we've coded up this function ourselves. Of course it will. Show scores. What are we going to find? Oh no, we've messed it up. NumPy has no spirit instead of square root. This is where we've messed up. NumPy, there we go. Typo, classic. Couldn't get it right the first go, could you, Daniel? Nope. So we'll see how our model does. We've just trained it here on a subset of the data. Beautiful. All right, look at that. So training mean absolute error. So valid, yeah, see here how I said the valid error will be slightly higher than the training. That's good. That means we're not overfitting. And our R squared for training and valid are far worse than the 0.987 we saw before, but that's all right because we're only training on a subset of 10,000 examples, not all 400,000. So we'd expect these metrics to be worse than if we were to set max samples to be none or train on all of the training data. Now, what we might do is see, this is our valid RMSLE of 0.29. I wonder where, if we were to compare that figure with the leaderboard, where would we end up? So there's about 425 teams in this competition. So if we were to submit our sample as it is now with our valid RMSLE score of 0.293, only on 10,000 samples, where do we end up? 0.293. Wow. We're in the top 100. Look at that. We're in the top 100 with just a simple model on 10,000 examples. So somewhere in here. All right. Now we've got an idea of how to train our model a bit faster. What we might do is try some different hyperparameters. And I'll let you think about it before we get into the next video. What's a way to find different hyperparameters rather than us having to manually adjust these hyperparameters of our random forest regressor? If you're not sure, don't worry, we'll cover it in the next video, but have a think. How have we found better hyperparameters in the past? Because that's what we're going to use for the next video. Okay, in the last video, we trained a model on a subset of data, aka allowing each estimator, so 100 estimators, to see 10,000 different data points rather than all 400,000 or so. And we saw a fairly big decrease in computing time. So our model trained faster. Now, what we might want to do is, because we can experiment a bit faster now, is try to find some ideal hyperparameters that are a bit better than what our random forest regressor defaults with. So let's have a look. And if you've had to think about it, you might have come across or thought of the idea of tuning, hyperparameter tuning with randomized search CV, something that we've looked at in a previous project and some other previous videos. So that's what we're going to have a look at. And so, if you're wondering what randomized search CV is, remember, we can always look up the docs, but what we'll do is, actually, maybe we'll just create a cell. Let's have a look at the code first. From Scikit-Learn, how would we import it? Model selection, randomized search CV. And remember, whatever machine learning model you're working with, you can always go insert the model name. So in our case, random forest regressor, hyperparameter tuning. And this will give you some information on how to tune your random forest regressor or your random forest in general. So that's one way to do it. The other way is, from the way that we've seen, is randomized search CV. Or actually, let's be real here, there are many different ways to do it, but if you remember what randomized search CV does, if not, that's okay. Randomized search CV. Go to the documentation. So randomized search on hyperparameters. Basically, we create a parameter distribution which kind of look like a dictionary, and randomized search CV is going to take our model, or estimator in Scikit-Learn terms, and search across this param distributions or dictionary for the best hyperparameters for our model. So that's what we're going to create. So different random forest regressor hyperparameters. And we'll go here, RF grid, nice and simple for the dictionary. This is the param distribution that I was talking about. And we might go over N estimators. Remember, if you're wondering where these came from, don't forget you can always search up here, random forest regressor hyperparameter tuning, and you'll find a fair bit of information on basically almost any machine learning model that you can think of different ways of how to tune the hyperparameters. Because again, this is not a perfect science. This is a whole bunch of trial and error of trying to figure out how things are going. And so what I'm doing here is I'm setting up a number of different values that randomized search CV is going to go through, try a certain number of calculations or combinations of them, and then figure out which ones achieve the best results, because that's what we're after, right? We're after a model that boosts us on the Kaggle leaderboard. That's what we're trying to do. With our default model with no tuned hyperparameters, we're sitting, and only 10,000 examples, mind you, that's the bigger one there. We're sitting at around 80th, so that's not bad. So what else are we tuning here? We've got number of estimators, max depth. These are all different parameters of the random forest. Min samples split, min samples leaf. And then we'll go max features. That's another good one. 0.5, 1, square root, auto. And then we also might go max samples. So we might also set this to 10,000 because we saw that before. Max samples increase how fast our model can find patterns in the data because it's only looking at 10,000 random examples rather than 400,000 that's in our training set. So in the spirit of trying to reduce the time between experiments, we'll set that to that. Instantiate randomized search CV model. We'll call this RS model really creatively, randomized search CV, and we'll pass it a random forest regressor with n jobs equal -1 and also random state equal to 42 for consistency. Remember, that's similar to setting NP random seed. And then we're going to pass it our param distributions, which is the RF grid, which is what we've just instantiated up here. And n-iter, we usually do it for about 20 or so. Oh, well, I like to do it for about 20 or so for the first time, but we might change that. We might see why. CV equals 5. Remember, that's cross-validation. Verbose equals true. And the reason why we're going to reduce this, we'll probably only do it. How much time do we have? Maybe only 2. Reason being is you might... Oh, what has happened here? 2. Maybe that went really fast. I'm not sure why. We'll check that in a second, but that's all right. Maybe 5. 5's enough. Because I've already gone through this process, but I've set n-iter to 100, but that took like 2.5 hours on my machine. So you could set this to whatever you want, whatever you have time for, but start low, because if we were to set this to 100, this cell might run for a couple of hours, and say if we were going home, we might set this to run for 100 and run overnight or something like that. Or if we had a lunch break, we might set it to run over a lunch break. That's what I used to do when I was working at a technology company in my city. I would run models over my lunch break, and while I was eating food, and the computer was just calculating away. In our case, we're just going to set this to 5. And what we'll do... Oh, that's why it ran so long, because we didn't even fit it. That's why this time is so small. rsmodel.fit. So what this is going to do... Actually, 2's enough then, because I thought this confused me, but I realized we didn't fit anything. That's why it went so fast. So, this is what we can do. We go fit the randomized search CV model. What this is going to do, it's going to fit 2 iterations. So randomized search CV is going to pick 2 different combinations of parameters from here, assign them to our random forest regressor, and then fit it to the training data. And remember, it's only on 10,000 samples for the maximum. And it's going to tell us, well, we'll be able to find out in a second, which are the best parameters. So because we're doing 2 iterations and we're doing a CV value of 5, there's still going to be 10 different fits. So this may take a minute or so we might time travel again. And I know we said we can only time travel every so often, but we unlocked a superpower going through this project because we're doing so well. We'll time travel until this cell is done. And we're back. So that took my MacBook Pro just under 2 minutes, right, to try out 2 different iterations with 5-fold cross-validation across a bunch of different hyperparameters. And now, even though this took about 2 minutes, it's still far less than our original 7-minute model trial that we did right in a few videos ago, because we've set max samples to equal 10,000. And now, because we have a trained model with randomized search CV, we can find the best model hyperparameters that randomized search CV found for us. And remember, we've only set this to 2. So if you have more time or more compute power, you might set this to something like 100 and find the best parameters from that. But we're only doing 2 for this case. And we go here, RS model dot best params. It's going to tell us, okay, so this is what the best parameters that it's found. 90 estimators, min samples split 16, min samples leave, 10,000, max samples because that was only one value, max features auto, max depth 10. And now remember, these might not be the best model hyperparameters because we've only searched for 2 different combinations, but we're going to work with them for now. Evaluate the randomized search model. Show scores, our beautiful show scores function, we're going to pass it the RS model. Now we may or may not see an improvement here in our evaluation metrics that we've used before. Yeah, so we actually see that this has worsened. That's okay, right? Because, as I said, we've only tried 2 different combinations. And now, in a past notebook, in a past project, when I was setting up for this project, I have actually, as I said, tried n iter equals 100. And I took a little break and I went and had some food because it took my computer just over 2 hours. And so we'll have a look at the best hyperparameters my computer found in 2 hours of searching, and we'll have a look at how they go in the next video. In the last video, we saw how we might find some of the most ideal hyperparameters for our random forest regressor, but we only set the number of, or in my case, you might have done this differently, you might have had some more time, but in the essence of time for recording these videos, I only set n iter to 2. However, in a previous experiment, aka step 6, I set n iter to 100 and found some more ideal hyperparameters than what we have here. So that's what we'll do. We're going to, in this video, train a model with the best hyperparameters. And we'll put a little note here. We'll go, note, these were found after 100 iterations of randomized search CV. And now, if you were to do something like this, like 100 iterations of randomized search CV, you still may find different hyperparameters, potentially better hyperparameters. The hyperparameter searching, or like finding the best hyperparameters for a model, is, as we've talked about before, it's not an exact science. It involves a lot of trial and error, a lot of experimentation. So for this one, you're just going to have to kind of trust me that I've run this 100 iterations. It took a couple of hours on my Mac. So I'll just show you which ones we found. So most ideal hyperparameters. And that way, once we've gone through something like this, a randomized search CV to find some ideal hyperparameters, because this was only, I'm scrolling back and forth here, because this was only trained on 10,000 examples, what you'll probably do is use randomized search CV to find some ideal hyperparameters across a space like this, on a subset, because otherwise it would take hours and hours and hours, and then retrain a model on the full data set, which is what we're about to do now, with the most ideal hyperparameters that were found in randomized search CV. So let's call this one ideal model, and we'll set it up here. Random forest regressor. So in my case, n estimators was 40. Now this is interesting, right? Because the default in random forest regressor, if we go here, Shift Tab, the default is 100. So it's actually, from the randomized search CV, it's actually found that 100 estimators weren't required. So 40 still provides pretty good results. Min samples leave was found to be 1. And then min samples split was found to be 14. And then max features was found to be 0.5. And n jobs, of course, we're going to set to -1 because we want our computer to use all of the processes that it has. Well, in my case, I do. Max samples equals none because why? We want to train on all of the data. So we set max samples to none, aka it will train on as many samples as possible. And now we're going to fit the ideal model because we've just instantiated above. Ideal model dot fit on the training data, xtrain, ytrain. And now this may take a couple of minutes. So what we'll do, I'll run this cell. And again, we're going to time travel. And once the training is complete, we'll be able to see how long it took because we've got time. And then we'll evaluate our model. Beautiful. So that took about 1 minute and 14 seconds. Now that's on the entire data. And the reason being is probably the main reason is because n estimators is 40 rather than 100. So what that means is the random forest is building 40 smaller little models rather than 100. So almost, 2.5 times less. And I did forget one parameter that we probably should have put in here. Random state equals 42. I'm not going to rerun the model now, but just so it's there, I'll put a little comment here. Random state. So this is so if we were to set a NumPy random seed, same thing. Random state, so our results are reproducible. Is that how you spell reproducible? Yes, it is. Beautiful. So if I was to run this cell again over and over and over with random state set to 42, we would get the same model being fit. But that took about 1 minute, 14 seconds on my computer. It may take a little bit longer, a little bit shorter on your computer, depending on how much processing power you have. And if you're running randomized search CV a number of times more than what we've done up here, you may potentially find different parameters to what I've found here. And if you have, I encourage you to share them so other people can try them out, and we'll evaluate it to see how they go, to see whose parameters are the real best ones. So let's check it out with our handy show scores function, and we'll pass it our model that we just trained. Shift and enter there. Beautiful. And because this is trained on all the data, we should see a significant improvement over the model that we trained before. So let's go up. Here we go, RS model. Okay, what we might do is bring these closer to each other. So we can go scores for ideal model, trained on all the data. And let's go here, scores on RS model, only trained on 10,000 examples. The exact same line of code, we ran a couple of cells up. I'm just doing it here so we can directly compare them. All right, so let's look at here. The valid RMSLE is probably the one we want to pay most attention to. As you can see with our ideal model, in 1 minute, 14 seconds of training time, it's gone through 400 or so thousand rows and reduced the valid RMSLE, yep, far out, that's a mouthful, by, what is it, about 0.8. So that's pretty damn good. And if we saw with this, we were already doing well on the Kaggle competition with our original model. Let's see where our new and improved one, which is our ideal model. So we're looking at this here. Valid root mean square log error, 0.246. Where does that get us on the leaderboard? 0.246. All right, so around about there, so 30. So we're almost in the top 30 on the Kaggle leaderboard, just in a model that took a minute to run. And going through here, we're like, this is a random forest regressor straight out of Scikit-Learn. That's pretty damn impressive, and we haven't really done an incredible amount of data manipulation. We've turned our data into numbers, we've filled missing value, but we're already getting some incredible results. So what we'll probably do is leave our ideal model there. We could search for longer with randomized search CV up here and find some better hyperparameters and probably slightly improve our model even more, maybe push us right into the top 25. That'd be pretty cool. But what we might do now is see how we'd make a submission to Kaggle. So what does this mean? So if we come here, how do you even get on the leaderboard? Well, if we go here to data, to get on the leaderboard, we have to make some predictions on test.csv. So right now, our predictions are on valid.csv, but all of these scores on the leaderboard, so really we are just guesstimating where we'd end up because we're predicting on valid CSV at the moment. We're evaluating our model on a validation set. But if we come back to overview and evaluation, what we have to do is submit a submission file. So, okay, submission file should be formatted as follows: sales ID, sale price. So that's what we probably might do now. We might import the test data set and format it in a way so we can use our machine learning model on it and create an example submission in the format that Kaggle is asking of us. So that sounds like a good plan. Now we've got an ideal model. We'll use that to make predictions on the test data set. Now we've got an ideal model that is performing pretty damn well on the validation data set. So valid RMSLE is the metric we've been paying attention to because that is the evaluation metric for this particular Kaggle competition. Of course, if you're working on a different problem or a different set of data, you may have a different evaluation metric that you're trying to improve. But in our case, we're doing pretty well. So let's use our ideal model to make predictions on test data. There's a little tidbit in this section that's really important to remember, and we're going to come across it in a second. So first of all, we're going to have to import the test data. Now, if we have a look in our data folder, so this is just in the Jupyter home because we've created a project folder for this particular project, and we've downloaded our data, put it in here. Inside here, there's a data set which is test.csv. So this is what we're going to be using. And if we come back to Kaggle, it tells us test.csv is the test set which won't be released until the last week of competition. Well, we've got it at the moment since this competition has already passed. It contains data from May 1, 2012 to November 2012. Okay, so it's about the 6 months or so after our validation set. Beautiful. And our model's performing okay on the validation set. So what we might see how we can make predictions on this future 6 months of data. So we'll go df test equals pd.readcsv. We're just going to do it the exact same we did at the beginning with our train and valid data set. Blue book for bulldozers. Wonderful. And it's called test.csv. And we'll pass in low memory equals false. And we're also going to pass dates because remember, we haven't done any manipulation to this data set like we have to our other ones. We'll see where that comes in a moment. And then we'll check df_test.head. Oh, what's happening? Oh, typos. Beautiful. So this looks familiar. It's something that we've seen before, except now this time the test data set is missing the sale price column. And the reason being is because that's the column we're trying to predict. So why don't we see if we can do that? So we go test preds equals ideal model. We'll use our ideal model this time. Model.predict. Our ideal model has been performing the best. And we should be able to just go pass it the whole data frame, right? Because this will be our X values and we don't need to drop any columns because it doesn't have a sale price column. So let's see what happens. Actually, I put a little comment here. Make predictions on the test data set. And I just thought of a little challenge. Before we run this cell, I want you to kind of think about what might happen. So our machine learning model, it's been trained on a particular data set, and now we've imported the test data set. What's going to happen if we try to make predictions on this data set? Based on, I'll give you a hint, based on the data that our model has been trained on. And if you're not sure, that's fine. We're going to see it in a sec. We should see it right now. Oh, there we go. Value error. Okay, what's happening here? Could not convert string to float. Oh, okay. So if you remember right back up the top, let's scroll back up through our beast of a notebook that we've been working through. What did we do before we could train a machine learning model? We saw that a similar error when we first started. Right up here when we started modeling. It'd be great if I could find it. Our model didn't work. Here we go. Okay. Build a model. So dftemp.drop could not convert string to float. So the same error message as what's below. Now the reason being this has happened is, what do you think? Well, it's because when we imported our original data set, we did some manipulations to it. What did we do? We made sure our data was numeric and we made sure there were no missing values. So what we've done now is we've imported df_test. It may have some missing values, which it does, and it might not be all numeric. And far out, we've done a fair bit of data processing here. And if we check the columns, so these are all the features, but if we check out xtrain.columns, oh, don't need brackets there, we notice that the column lengths are different. So there's 102 columns in our xtrain, whereas in df_test, what do we got here? We saw it up here before when we did .head. 52 columns. So the reason why our machine learning model can't predict on the test data set at the moment is because it's not in the same format as the model was trained on, or as the data set the model was trained on. So that's what we're going to have to do. All right, let's get rid of these here. And so how could we do this? So we might go pre-processing the data. In other words, getting the test data set in the same format as our training data set. Wonderful. And so how might we do this? So what we might do, I think, is create a function for doing so. So if we were to import a new data set, say a test data set, we actually did some manipulations to our training data set. We could take those functions that we did on the training data set and just do the exact same thing on the test data set. So that way, they're both the same. Does that make sense? Let's see it first. Let's see if we can do this. So pre-process data, we'll pass it a data frame. We'll leave a little note here. So performs transformations on df and returns transformed df. Simple, right? We want to create a function which takes a data frame of some sort. It does a bunch of manipulations on that data frame, and then eventually it's going to return that data frame. So now we're going to have to fill in all the transformations that we did originally to df_temp in here. And so we can do that by going up. We might have to do a few copies and pastes here. So remember, right back up the top. So this is a little rule, a little tidbit. What you do to the training data set, you're going to have to do to the test data set. So that's a machine learning tidbit there. Okay, so here's the first big set of manipulations that we did. We might copy that. Wonderful. And we can just remember this line. So we've added some information here based on the date time column, sale date. And then we removed it. So they're the first two steps that we have to do. Okay, we'll scroll right down to the end of our notebook. It's going to be a lot of scrolling in this video because we did three major things, right? We added some information here to the date time, or we extracted, that's probably a better idea. We extracted information from our date time column and added it to the data frame. So we might go df.drop. And after we've done this, we'll drop the sale date column and we'll go axis equals 1 and in place equals true. Wonderful. And we have to remove .temp from all of these because we're only using df. So a little trick here is by moving your cursor and holding down Command if you're on a Mac, or maybe it's Control if you're on Windows. And we can just go backspace here. Wonderful, right? Because we're not working with df_temp, we're working with df, so any arbitrarily named data frame will work with our function. So the next thing we did was we need to fill the numeric rows with median, and we also filled categorical missing data and turned into numbers, and turn categories into numbers. So that's what we have to scroll back up and find. Okay, let's do that. First we'll get the missing missing numericals. Luckily, we've laid our notebook out. We've added these headings here so that we can see what we were doing. This is all part of helping yourself out, right? So fill numeric rows with the median. We actually need all of this code here. We'll copy that. Beautiful. So this is where comments and different headings in your notebook can really help your future self out, is when you want to functionize things and clean things up. So there we go. Again, we have to remove df temp. So we'll go df temp, we don't want that. Df temp, we only just want df. Okay, beautiful. And we still need to fill categorical missing data and turn categories into numbers. Now let's just see if we can remember how to do this rather than having to scroll back up, because we've done enough scrolling, to be honest. So we can do this if not, if we remember, if it's not a numeric type, that's how we did it. Type.is numeric dtype content, because we're looping, we're in this same loop here, content. We want to go df label plus underscore is missing, yes, equals, so it's going to check if it's null. If it's null, we want to add a label that a label is missing, that particular data point is missing. And remember how we add +1 to the category code, because pandas encodes missing categories as -1. So this is where we can go df label equals pd.categorical, so turn it into a categorical. So turn the content of a particular column into a category, and then access its code, aka turning it into a number, and then +1. All right, not a bad function. So this is what kind of happens in a notebook workflow, right? Is that up here, you could probably classify most of this as pretty messy. We've helped ourselves out with different headings and whatnot and comments. However, as you sort of get further into the process, you'll start to build these helper functions. So you're collating a whole bunch of different steps into a function so that it really succinks things in the notebook, and you can just call a function like this, much like our show scores function, and it does a process that's going to be the same every time, rather than having to scroll up through the notebook and find something in a different cell. So now we can hit Shift Enter on that. Oh, what's happened? Expected missing block. I didn't think we needed one. Oh, here. That's where we need it. We needed indents here. There we go. Ah, classic. This is what happens when we copy and paste code, right? The formatting isn't always perfect. Beautiful. So we have a function here that's going to pre-process some sort of data frame. It's going to add some information based on the sale date column. It's going to fill numeric rows with the median. It's going to turn the missing categorical data into a 0 value, and the rest of the data into their category code number. Beautiful. So it's going through a few steps, but that's all right. We've functionized it, so it's all going to happen together. And now, what might we do here? Actually, a good question is, where might this function break? I might leave you on that for this video to save it from getting too long. I want you to have a look at this big function that we've created and think about, if we passed it our training data frame, how might it work? And then if we passed it our test data frame, right, df test, which is up here, we passed it this data frame, how might it break? We'll answer that in the next video. Okay, so now we've got this behemoth of a function that's going to pre-process our data. Let's try run our df test that we just imported up here and tried to make some predictions on. So we imported it here, tried to make some predictions on it, but it didn't work because it's not the same format as the training data. Let's run it through our pre-processed data, and hopefully, if we've done it correctly, it's going to make the same changes on df test as we have on the training data. So let's go here, df test equals, or actually we'll put a little comment here, process test data, and we might just reinstantiate to make sure that we'll hit Shift Enter here, just to make sure that these cells have run. I've been notorious in writing a function and then not running the cell, so it actually doesn't work. Pre-process data df test, and then we should be able to check it out by going df test.head. Okay, 101 columns. Oh, that's looking better. So we're up We're up a fair few columns from what we started with. We go back here, we started with 52 columns. Now if we go through here, okay, on the end there's a fair few missing. All right, okay, so it's going to be missing the sales price column. Okay, that makes sense, but still a different shape to Xtrain. So we've got 101 versus 102 columns. And now if you remember in the end of last video, I asked to have a think about where this function might break. And if you're not sure, that's fine. I've stumbled across this many of times, right? In the process of trying to make our training data or our test data in the same format as our training data. And what it is that the test data, when we imported it, is slightly different to the training data. As in, let me demonstrate. We're doing model-driven EDA, so we'll try to make a prediction again. So make predictions on updated test data. We go test preds equal ideal model dot predict df test. We get value error again. Hold on, I just pre-processed it. What's wrong? Let's check it out. Number of features of the model must match the input. Model n features is 102. Okay, that's what our model has been trained on. And input features is n101. Well, we just saw this when we went xtrain.head. That's 102 columns. So there is a difference in the number of columns that our test data frame and our training data frame have. Hence why our machine learning model doesn't work. So how would we figure out where the difference is? Well, we can do that using the columns attribute and turning them into sets. Let's have a look. So we can find how the columns differ using a Python set. If you've heard of sets, they're basically a list with only unique values in them. So we can go set xtrain.columns minus set df test.columns. And now this is going to tell us which columns are incorrect. Auctioneer ID is missing. So our df test has no column, auctioneer ID is missing. So what that means is when we imported our test data frame, according to our function, it didn't have any auction ID values that are missing. So what we can do is manually update a column on our df test data frame to have all false values for auction ID is missing. Because the reason being there is no column auctioneer ID. Man, if you can't tell, I'm having trouble saying auctioneer ID. The reason why our df test data frame has no column named this, right? This here, what I'm highlighting, is because all of the auctioneer ID values were filled in df test. So what we have to do is manually adjust df test to have auctioneer ID is missing column. And this is just as simple as adding df test. We'll just copy this here. So we'll create a new column and we're going to set it to just false because it had no missing value. So df.head, and now, df test.head, wrong data frame. So df test.head, 102 columns, beautiful. So if we come right to the end, it should have auctioneer ID is missing. Wonderful. So this means, finally, now our test data frame has the same features as our training data frame. We can make predictions. Let's do it. So make predictions on the test data. Wonderful. So we'll go test preds equals df test. Ideal model. So our ideal model dot predict df test. Boom, that worked. And now let's have a look. These should all be like prices, an array of prices, and it's going to be, how big is our test data frame? So these are all the sale prices that we've predicted. So 12,457 samples, but it's not going to help us in an array format because Kaggle expects it to be in a data frame with 2 columns, sales ID, sales price. So what we can do, we can turn it into that. So format predictions into the same format Kaggle is after. We've made some predictions, but they're not yet in the same format Kaggle is asking for. Now we'll just link that here. Evaluation, so we know we could go there. Okay, so how would we do this? Well, we need the sales ID column and we need the sales price prediction. So what we might do is just make a simple data frame, df preds equals pd.dataframe. So empty data frame, df preds. The sales ID column is just going to be sales ID from df test. So we can go equals df test sales ID. Oh, that needs to be the same capitalization. And then the sales price is going to be test preds. So just our array here. And then let's have a look at df preds. Boom. There we go. Look at that. How exciting. We've got a submission that we could submit to this Kaggle competition, but at the moment this Kaggle competition is no longer running, but that's an example of how you could get your data in a format that it's asking for. And then to export that, how might you do that? Well, if we wanted to export this to CSV, we might do something like df preds dot to, I'll put a little comment here, export prediction data to CSV. We'll put it into data and we'll go test predictions, something easy, .csv, and index equals false. Wonderful. Or actually, no, this is Blue Book for bulldozers. We'll see if that'll export. Let's go up into our data folder. Do we have that? Test predictions.csv. Wonderful. Okay. And so now we've got some test predictions. We can't really evaluate these though because we don't have the ground truth labels for the test dataset. That's why we were doing our evaluation on the validation dataset. So what we might look at, one final thing to wrap up this project, is feature importance. So we've just used the patterns, where is it? Here. When we made predictions on the test data, we've used the patterns that our model has found in the training dataset to make some predictions on sale price. And these patterns are how each of these columns contribute to predicting the sale price. So a logical thing or a good idea to figure out would be, in feature importance, what columns here or what features meant the most when the model was trying to make a prediction. So let's do that in the next video. Since we've built a model which is able to make predictions, we've done some on the test data set, we've exported them. Now, the people you share these predictions with, or in fact yourself, I know in my case, I'm very, very interested, might be curious of which parts of the data led to these predictions. So this is where feature importance comes in. Feature importance, in other words, it seeks to figure out which different attributes of the data were most important when it comes to predicting the target variable, or in our case, the sale. Let's write that down here. Feature importance seeks to figure out which different attributes of the data were most important when it comes to predicting, let's put this in bold, target variable. So in our case, it's the sale price. All right, so how might we do this? We know we're using a random forest regressor. We've seen in a previous video in the classification project, as well as the Scikit-Learn project, some Scikit-Learn models have the attribute feature importances. But if we didn't know, if we're using a model that we weren't familiar with, maybe we could go something like this. So random forest regressor feature importance. Beautiful. So maybe this will give us some good results if we were to go and explore these. We've got the Scikit-Learn documentation, that's always helpful. So if we were looking in here, maybe we might search for, wow, it knew what we want. Feature importances. Return the feature importances. The higher, the more important the feature. Let's see what that actually does. So let's take our model. So find feature importance of our best model. So we'll take our ideal model and we'll find feature importances. Wow. Now that returns a fairly large array. A whole bunch of different values here. Some of them are 0. Some of them are pretty low, 10 to the negative 6 there. But what does this have in common? Let's check out the length of this. What does this have in common with our training data set? 102, 102. What we might infer is that we've got 102 columns here and we've got 102 values here. So we're getting a value for every feature. So sales ID would map to this, and machine ID would map to this. Now we could make a dictionary by going xtrain.columns and intertwine these values, but I don't know about you, I prefer to see things visually. So let's why don't we make a helper function which helps us do that. So we might make a helper function for plotting feature importance. So we can see it visually. So we'll go here, def plot features, and we might take a list of columns and a list of importances, and we're gonna set n to 20. Now this will make sense in a second because we have 102 values here, but realistically, if we wanna look at a plot, maybe we only want the top 20 values. And I mean, that's why we set it so we can adjust it with this little function here. Helper functions are great. I should have started using functions earlier. Writing functions saves a lot of time, put it that way. I used to just write the same line of code over and over and over again in different cells, but I've started to get into the habit of writing functions for different uses. So what we might do is use a little Pandas trick here called chaining. And what that means is just simply putting a number of different Pandas functions in brackets. And we'll see that in a second, because we're going to make a data frame called df, and it'll have 2 columns. Features can be columns, and feature importances can be importances, right? So we're just creating a data frame here, and then we're going to call sort value. So see here, these are still within the brackets, these 2 here. So what this means is it's going to do pd.dataframe and .sort values in one hit. And we want to sort it by feature importances. And we want ascending equal to false. So we want it to go from highest to lowest. Yep, that makes sense. And then we want to reset the index. Drop equals true. Right. Actually, this bracket should be down here. So because we've got a bracket here and 2 dots, that means it's just going to do these 3 Pandas steps in one hit. And now we need to plot. So plot the data frame we've created. So what we might do is go fig ax instantiate a plot plt.subplots. And then we might do a horizontal bar because in my experience plotting features, it looks really good on a horizontal bar. And now we only want up to n. That's why we have n there. So that's going to be the first 20 examples, and the same with feature importances. We only want up to 20. So the first 20. Then we're going to set the y label. So ax.set y label to features. Because it's a horizontal bar, x and y are rearranged. And we go ax.set x label, add some communication to it. We'll put feature importance down the bottom. Let's see what this looks like actually. So we've got our helper function, we've just run it there. All we have to do to call this is go plot features, and then we'll pass it columns. So we just want the columns from xtrain because that's a variable there. And then the feature importances are just the ideal model dot feature importances. Let's see what this looks like. Okay. So we've got the features on the left here, their value here. I want the top one, the most valuable feature, to be at the top. So what we might do is ax dot, how do we do it? Invert. Can we invert? I think it's ax dot invert y-axis. Maybe that's not a function. If in doubt, run the code. Invert y-axis. That didn't work. Maybe it is a function. Boom. If in doubt, run the code. Trust your instincts, right? That's how you learn things. You practice by running it without looking up. If in doubt, you can always look it up, right? You can always ask how to invert a horizontal bar plot in Matplotlib. Google should be able to help. All right, so what can we infer from this? So there's a fair bit going on. We've got about 20 different features here. So it's saying that year made. Let's have a look at our xtrain.head. Let's get that in here. So it's saying that the year that the bulldozer was made is the most important feature based on the ideal model. And then the product size, what is that? Let's look at our data dictionary. Product size. Product size. Don't know what this is. Okay, that's great. The size grouping for a product group, subsets with product group. This is an example of where you maybe need to do some more research and figure out what features are what. If you've got something like this in your data dictionary, you might have to reach out to like a subject matter expert, or we could just go xtrain product size. Maybe we check the value counts. Okay, so there's 1, 2, 3, 4, 5, 6 different sizes. Now 0 is going to be missing. So there's a lot of missing values there. All right, but maybe this doesn't really tell us much. So maybe we could do it on our original data frame. There we go. All right, so the product size, well, that kind of makes sense that the product size is influencing the sale price. Sale year, enclosure, also doing a fair bit of damage there. Enclosure, value counts. Okay, so that's, that doesn't really make much sense to me. So then we go back to the data dictionary. Maybe we find enclosure. Machine configuration. Does machine have an enclosed cab or not? All right. So maybe we need to figure out what these different values might mean. But this is the kind of exploration you probably do towards the end of after you've built a model, right? Is bringing this to someone after you've made some predictions. You might take this in a sort of a presentation. So maybe you're meeting with a client or meeting with another team member or something. You're going, hey, this is what the most important features our model has found. Does this agree with your sort of intuition, with what someone already knows about the data? Does this make sense? If a model is using these features to derive its predictions, does this make sense? Or this information here might influence how you go about collecting data in the future on your bulldozer sales. So you might put a bit more effort into the values here that are contributing most to predicting the sale price of a bulldozer in the future. The last probably question that I'll leave you with is we've kind of just glazed over it a little bit, but I want you to do a little bit of research is why might knowing the feature importances of a trained model be helpful? That's a finishing question. So question to finish. This is going to involve some research. Why might knowing the feature importances of a trained machine learning model be helpful? So that's going to finish off this project 2. Finish off with a little question here. What you might want to try and do is, if you've followed along with all of these steps here, you might want to see how far you can go with hyperparameter tuning. So something like this, maybe you could leave this run for a while on your computer, see what it finds out, see if you can improve the valid RMSLE score, and see how far you'd get up on the leaderboard. Now, if you do reach a point where you're not really improving with a random forest model, what a final extension may also be is final challenge is what other machine learning models could you try on our data set? And what that might involve is something like searching for the Scikit-Learn machine learning map. So what we've done is we've gone through this and we've gone to regression problem. We found ensemble regressors and we've used a random forest. Maybe you want to try another one of these regression models using the formatted data that we've worked through in this notebook. So I'll leave a little hint here. So hint, check out the regression section of this map, or try to look at something like catboost.ai or xgboost.ai. So these are two extra resources, so extra curriculum. Of course, they're optional at this point because once we've started to work through these sort of projects, now we've gone end to end on a full machine learning project. Your next steps are kind of trying to figure things out on your own, taking what you've learned from here and then expanding on that. That's the kind of information, that's the kind of knowledge that is really going to help out, right? So rather than sort of always going through projects like this, it's doing some research and trying out new things. Remember step 6 of our little framework here, experimentation. That's the challenge I leave to you. But that being said, if you have made it this far, if you have gone through the entire project, congratulations. We've just gone end to end on a regression problem using machine learning. How cool is that? So have a look at the notebook, see what improvements you can make. If you have any questions whatsoever, feel free to ask them, leave them in the Discord chat or in the Udemy interface somewhere where you can leave a question, and we'll see what we can do from there. But congratulations, working through a first end-to-end regression project. How exciting. All the best.